Tonight, we are going to travel to the most colossal object ever measured in the known universe. Not a galaxy, not a nebula, not a cluster of a billion suns, a single star. One star, standing alone in the dark, so incomprehensibly vast that the moment you truly understand its scale, not just accept the number, but genuinely comprehend what the number means, something in the way you perceive the cosmos will shift permanently. There is no going back from this. Once you understand how large Stephenson 2-18 actually is, the night sky will never look quite the same to you again. But we are not going to begin there. We are going to begin somewhere much smaller, somewhere familiar, somewhere you have known your entire life without ever truly reckoning with what it is. Right now, at this precise moment, a star is burning approximately 93 million miles from where you are sitting. It has been burning for 4.6 billion years. It burned before the first fish swam in the first ocean. It burned before the first cell divided in the first warm pool of water. It burned before the Earth itself existed, before the dust and gas that would eventually become. This world had even begun to collapse inward under gravity. It will continue burning for another 5 billion years after every human being who has ever lived has been forgotten. And yet, in the grand catalogue of everything that exists in this universe, that star is ordinary, commonplace, an average object in an average location, notable only because, by the accident of proximity, it happens to make life on this particular planet possible. But here is what most people fail to appreciate. That ordinary star, the one that rises every morning, that warms the ground, that drives the weather, that makes the crops grow, that you have looked at your entire life without truly seeing that star is a thing of staggering, almost violent immensity. And it is still tiny. That is the story we are going to tell tonight. If you find yourself drawn to these journeys through the deep structure of the universe, if this is the kind of content that genuinely reshapes how you see the cosmos, take a moment and hit that like button and subscribe to this channel. It is a small gesture on your end, but it makes an enormous difference in allowing this work to reach other people who share the same hunger for understanding. Now, make yourself comfortable, clear your mind. We are going to go somewhere extraordinary tonight. Let's begin. The sun, you know it. You have known it your entire life. It is so constant, so ubiquitous, so embedded in the rhythm of every single day you have ever experienced, that it becomes almost invisible, not literally of course, but psychologically. The mind filters out what is always present. The sun rises, the sun sets, the light changes, the temperature shifts. You move through your day. The sun is simply there, a backdrop to everything, a given, something you stopped truly noticing years ago, the same way you stopped noticing the feeling of the floor beneath your feet. But consider what the sun actually is. Strip away the familiarity. Look at it as if you were encountering it for the first time. The sun is a sphere of plasma superheated gas, so energetic that electrons have been torn completely free from their parent atoms, leaving behind a churning, luminous sea of charged particles. At its core, temperatures reach approximately 27 million degrees Fahrenheit. That is roughly 15 million degrees Celsius. At those temperatures and pressures, hydrogen nuclei single protons are forced together with sufficient violence to overcome the electromagnetic repulsion that normally keeps positively charged particles apart. 4 hydrogen nuclei fuse into a single helium nucleus. In that fusion, a tiny fraction of mass is converted directly into energy, according to the most famous equation in the history of science. The sun converts approximately 600 million tons of hydrogen into helium every single second. Every second. And in that conversion, roughly 4 million tons of matter are annihilated, entirely transformed into pure energy that floods outward through the star's interior and eventually escapes from the surface as light, heat, and radiation. The energy you feel on your skin on a warm afternoon left the sun's core somewhere between 10,000 and 100,000 years ago, spent that entire time slowly diffusing outward through the dense solar interior, and then crossed 93 million miles of empty space in approximately 8 minutes before arriving at your face. The Sun's diameter spans roughly 864,000 miles. If you wanted to drive across the Sun at highway speed, say 60 miles per hour, and you could somehow survive the conditions, the trip would take approximately 1,640 years. You would need to lay 109 Earths side by side just to bridge its diameter, not stacked on top of each other, laid flat, equator to equator, in an unbroken line, 109 Earths. And that covers only the diameter. Volume scales with the cube of the radius. The Sun's volume is approximately 1.3 million times the volume of Earth. Every mountain on this planet, every ocean trench, every continent, every city, every forest, every living thing that has ever drawn breath, everything that has ever existed on this world, occupies a sphere whose total volume could fit inside the Sun more than 1 million times. Imagine emptying the Sun of everything inside it and filling it with Earths, packed as tightly as possible. You would need approximately 1.3 million of them before the interior was full. The mass of the Sun is roughly 2 followed by 30 zeros kilograms, 2 times 10 to the power of 30. That number is so far beyond ordinary experience that the figure itself communicates almost nothing. A more useful way to approach it is through proportion. The Sun contains 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every cloud of interplanetary dust. Every rock drifting in the outer reaches of the Oort cloud, billions of miles from the nearest light. All of it combined, the total mass of everything in the solar system that is not the Sun amounts to 0.14% of what the Sun holds. Jupiter, the largest planet, the gas giant so massive that it contains more mass than all the other planets combined, times 2. Jupiter represents roughly 0.1% of the Sun's mass. Earth represents approximately 0.0003%. The Moon, which has shaped our tides and our calendars, and the myths of every civilization that has ever watched the night sky, represents a fraction so small it barely registers in the arithmetic. This is the object that we call ordinary, an average star, a G-type main sequence yellow dwarf. Nothing special. In the Milky Way galaxy alone, there are between 100 billion and 400 billion stars. Among them, the Sun is unremarkable. It sits in the middle of the mass distribution, larger than the most common stars, smaller than the massive ones. An object that astronomers would pass over without a second thought if it were not for the fact that it happens to host a small rocky planet with liquid water and a thin layer of complex organic chemistry on its surface. On any cosmic ledger, the Sun is a footnote, typical, average, medium-sized in every meaningful way. And yet, standing on the surface of this planet, the Sun seems like everything. It is the source of virtually all energy flowing through the biosphere. Remove the Sun, and the Earth would cool toward the temperature of deep space within weeks. The oceans would freeze, the atmosphere would begin to condense and settle onto the frozen surface. The last living things would cling to hydrothermal vents on the ocean floor, drawing energy from the residual heat of the planet's interior. But even that would not last. Life as we know it is, fundamentally, a process of capturing and spending sunlight. The Sun is not merely a background feature of our existence, it is the engine of it. The Sun is 4.6 billion years old. It has been fusing hydrogen at its core for 4.6 billion years, and it will continue to do so for approximately another 5 billion years. At that point, the hydrogen in the core will be exhausted. The core will contract under its own weight, heating up as it does. The outer layers of the Sun will expand outward, cooling as they spread across an increasing volume of space. The Sun will become a red giant, swelling to perhaps 100 or even 200 times its current radius. Mercury will likely be consumed, Venus almost certainly. Earth may be grazed or engulfed, depending on how the mass loss during the red giant phase affects the orbital dynamics of the inner planets. The oceans will boil, the atmosphere will be stripped away, the surface will melt. Eventually, the Sun will shed its outer layers in a slow, luminous outflow, creating a glowing shell of expelled gas called a planetary nebula. The residual core will compress into a white dwarf, a dense, Earth-sized object no longer sustaining nuclear fusion, cooling gradually over billions and billions of years. That is the sun's destiny. A slow, quiet fade. Nothing dramatic. No explosion. No collapse into a black hole. Just a gradual dimming, spread across timescales that make the current age of the universe seem brief. That fate awaits our sun because it is average. It does not have enough mass to die violently. The truly massive stars, the ones that are many times heavier than the sun, the ones that burn through their fuel in millions rather than billions of years, those stars die differently, catastrophically, magnificently. And before they die, they do something extraordinary. They grow. The sun, as we have established, spans 864,000 miles across. That is the yardstick. That is the unit we will use for everything that follows. When astronomers want to express the size of a star, they frequently do so in solar radii, how many times larger the star's radius is compared to the sun's radius of approximately 432,000 miles. A star with a radius of 10 solar radii is 10 times larger than the sun in every linear dimension. Its volume, however, is 1,000 times greater. Because volume scales as the cube, a star with a radius of 100 solar radii has a volume 1 million times greater than the sun. A star with a radius of 1,000 solar radii, which already sounds impossible, has a volume 1 billion times the sun's. Keep that in mind, because the star we are building toward has a radius of approximately 2,150 solar radii. And the implications of that number unfold in stages, each one more difficult to absorb than the last. Before we arrive at Stephenson 2 to 18, however, we need to make one stop. We need to visit the star that for years held the record unchallenged. The star that first made astronomers truly reckon with what the upper limits of stellar size might mean. The star that made our sun look not just small, but invisible. That star is UY Scuti, and it is a useful place to pause, because understanding UY Scuti will give you the framework you need to truly appreciate what comes next. UY Scuti was supposed to be the biggest thing we had ever found, the ultimate answer to the question of scale, the object against which all others were measured. For years it seemed untouchable. It was wrong. But it was spectacularly, staggeringly, usefully wrong, in the direction of too small. We will go there next. UY Scuti. The name itself is unremarkable, a designation pulled from a catalogue, a string of letters, and a number that tells you the star's position in the constellation Scutum, the shield, a small and faint patch of sky sitting just south of the celestial equator. If you looked up at Scutum on a clear night from a dark location, you would see nothing special. A modest scattering of stars, none of them particularly bright, none of them drawing the eye. The constellation itself is one of the smallest in the sky, occupying a narrow strip of the Milky Way's dense central band. There is nothing about its appearance that suggests it contains something extraordinary, nothing to indicate that buried within that unassuming region of sky, behind layers of interstellar dust and gas, sits one of the largest single objects in the observable universe. UY Scuti was first catalogued in 1860 by astronomers at the Bonn Observatory in Germany. At the time, it was simply recorded as a variable star, a star whose brightness fluctuates measurably over time. Variable stars were a known phenomenon by the mid-19th century, and cataloguing them was routine work, the kind of careful, unglamorous astronomy that fills observatories with logbooks and filing systems rather than headlines. UY Scuti was assigned a number, noted for its variability, and largely set aside. Nobody in 1860 had any reason to suspect that this dim, distant, dust-shrouded point of light was anything other than one variable star among thousands. For the better part of a century, that is essentially what it remained, a data point, a catalogue entry. A star known to fluctuate in brightness with a period of roughly 740 days, brightening, dimming, brightening again in a slow rhythmic pulse, but not otherwise distinguished from the thousands of other variable stars scattered across the Milky Way. The technology to measure stellar sizes with any real precision did not yet exist in the form it would eventually take. Stars were points of light, and even with improving telescopes, measuring the physical diameter of something so distant and so small in angular terms was a problem that resisted easy solution. The breakthrough came gradually, through a technique called interferometry. The basic principle is elegant. Rather than relying on a single telescope aperture to resolve the disk of a star, which, for even the largest and nearest stars, requires resolving angles smaller than a millisecond, astronomers combine the light from multiple telescopes separated by large distances. By measuring the interference patterns in the combined light, they can extract information about the angular size of the star's disk with far greater precision than any single instrument could provide. It is the same principle that allows two ears separated by a few inches to locate a sound source far more accurately than one ear alone. Separation creates resolution. Using this and related techniques, combined with careful spectroscopic analysis, the science of breaking a star's light into its constituent wavelengths and reading the chemical and physical fingerprints encoded there, astronomers were eventually able to estimate the physical sizes of a number of the sky's largest and most luminous stars. And when they turned their attention to UY Scuti with modern instruments, what they found stopped them. The radius of UY Scuti, according to measurements published in 2012 and subsequently refined, is approximately 1,708 solar radii. Some estimates have placed it as high as 1,900. The uncertainties are substantial. Measuring the radius of a star 9,500 light-years away, embedded in a dense and dusty region of the galaxy, involves corrections for dust extinction, uncertain distances, and the difficulty of defining exactly where a star's surface ends, given that the outer layers of red supergiants are more atmosphere than solid boundary. But even at the conservative end of the estimates, even taking the lower figures and acknowledging the error bars, UY Scuti is a thing of almost hallucinatory scale. Let us work through what 1,708 solar radii actually means. The Sun's radius is 432,000 miles. Multiply that by 1,708, and you get a radius of approximately 738 million miles. Not diameter, radius, the distance from the center to the surface. The diameter, the full span from one side to the other, is approximately 1.476 billion miles. For context, the distance from the Earth to the Sun is 93 million miles. That distance, 93 million miles, the unit astronomers call one astronomical unit, the fundamental yardstick of the solar system, fits inside the radius of UY Scuti approximately 8 times. The radius, not the diameter. This means that if you placed UY Scuti at the center of our solar system, in the position currently occupied by the Sun, its surface would extend past the orbit of Jupiter. Jupiter, the gas giant that sits 484 million miles from the Sun. The planet so large it contains more mass than all the other planets combined. The planet whose gravitational influence has shaped the architecture of the entire solar system over billions of years. Jupiter would be inside UY Scuti, not orbiting outside it. Inside it, Saturn's orbit, at roughly 886 million miles from the Sun, would be close to the star's surface. Depending on which size estimate you use, Saturn might just be grazed by the outer atmosphere of UY Scuti, or might sit just beyond its photosphere. But Jupiter, Mars, Earth, Venus, Mercury, all of them, every inner and middle part of the solar system as we know it, the entire region of space in which every planet capable of supporting life currently resides, would be submerged inside the body of this single star. Think about what that means in human terms. Every sunrise and sunset you have ever seen, every ocean you have ever looked at, every mountain range, every city, every face you have ever recognized. All of it exists on a planet that would be consumed, vaporized, annihilated, not even leaving a trace of ash inside the outer layers of UY Scuti. The planet would not survive long enough to fall to the center. It would dissolve the moment it crossed the star's diffuse outer boundary, the plasma density and radiation pressure increasing around it as it fell inward, until there was nothing left to fall. Now imagine how long it would take to fly across Scuti. Commercial aircraft cruise at roughly 575 miles per hour. At that speed, flying in a straight line through the diameter of Scuti 1.476 billion miles would take approximately 293,000 years. If a commercial flight had departed from one side of Scuti, the moment modern humans first walked out of Africa, roughly 300,000 years ago, it would be arriving at the other side approximately now. The entire history of our species, every migration, every invention, every civilization, every war, every artwork, every discovery would have elapsed during the crossing of a single star. Even at the speed of light, 186,000 miles per second, the absolute maximum velocity permitted by the laws of physics, the speed at which photons travel through vacuum crossing the diameter of Scuti takes approximately 2.2 hours, not days, not weeks, hours. But consider how long 2 hours of light travel represents when you are inside a star. Every second, light is covering 186,000 miles. In 2 hours and 13 minutes, it covers the full width of this object. There is no vehicle, no spacecraft, no technology conceived or conceivable in the current state of human science that travels at the speed of light. The fastest spacecraft ever launched by humanity, NASA's Parker Solar Probe, reached speeds close to 430,000 miles per hour at its closest approach to the Sun. At that speed, the fastest any human-made object has ever moved, a velocity so extraordinary that the probe must use a specially designed heat shield just to survive the thermal environment near the Sun. Crossing the diameter of Scuti would take approximately 391 years, 14 generations of human beings, one after another, each inheriting the mission from the last, each born and living and dying aboard a vessel that would still not have crossed a single star. The volume of Scuti is approximately 5 billion times the volume of the Sun. 5 billion suns could fit inside Scuti. Recall what we established about the Sun. 1.3 million Earths fit inside the Sun. 5 billion suns means, by extension, approximately 6.5 quadrillion Earths, that is 6.5 followed by 15 zeros, could theoretically be packed inside the volume of Scuti. The number is so large that it resists any intuitive grasp. You can write it down, you can say the words, but there is no mental image that corresponds to 6.5 quadrillion of anything. Scuti is classified as a red hypergiant, the most extreme category in the taxonomy of stellar types. To understand why, it helps to understand the basic spectrum of stellar evolution and the role that mass plays in shaping a star's destiny. When a star forms from the gravitational collapse of a molecular cloud, a vast region of gas and dust drifting in interstellar space, the mass that accumulates at the center determines almost everything about the star's subsequent life. A star like the Sun, with modest mass, burns slowly and steadily for billions of years, fusing hydrogen into helium at a rate calibrated to last for the long haul. A star with 10 times the Sun's mass burns far more intensely. The relationship between mass and luminosity for main sequence stars follows roughly a power law. Doubling the mass more than doubles the luminosity. A star 10 times more massive than the Sun is not 10 times brighter, it is closer to 3,000 times brighter. It burns through its fuel correspondingly faster, living for millions of years rather than billions. Stars with masses above roughly 8 solar masses will, after their main sequence lives, expand into red supergiants. The mechanism is the same as the Sun's eventual red giant phase, but operating on a far grander scale. As the hydrogen in the core is exhausted, the core contracts and heats, igniting hydrogen in a shell around it. The outer layers respond to the increased energy output by expanding outward, cooling as they spread across a larger surface area, shifting from the blue-white of a hot young massive star toward the deep orange and red of an extended, diffuse, cool outer atmosphere. The star inflates, and for the most massive stars, those with dozens or even hundreds of solar masses, burning through their reserves at rates that make even ordinary massive stars look conservative, the inflation can be extraordinary. Scuti is believed to have a mass somewhere in the range of 7 to 10 solar masses at present, which sounds surprisingly modest for such an enormous object. But this apparent paradox dissolves when you understand that massive stars shed mass prodigiously throughout their lives. Through powerful stellar winds, through episodic eruptions, through the intense radiation pressure that literally pushes material off the surface, very massive stars can lose a substantial fraction of their initial mass over their lifetimes. Scuti is believed to have started considerably more massive and has been shedding material for millions of years. What remains is a bloated, diffuse, extended object, enormous in volume but diminished in mass, the stellar equivalent of a balloon inflated to its maximum size before the air begins to escape. The surface temperature of Scuti is approximately 5,500 to 3,400 Kelvin, far cooler than the Sun's surface temperature of approximately 5,778 Kelvin. This is counterintuitive at first. How can a star so much more luminous than the Sun have a cooler surface? The answer lies in the relationship between total luminosity, surface temperature, and surface area. A star's total energy output is the product of the energy radiated per unit area, which depends on temperature to the fourth power and the total area of the radiating surface. Scuti is so enormously larger than the Sun in surface area that even at a lower temperature per square meter, its total output is vastly greater. The star is approximately 340,000 times more luminous than the Sun. If you replace the Sun with Scuti at the same distance, keeping Earth at the same 9.3 million mile remove, the new Sun in our sky would be approximately 340,000 times brighter. The day side of the Earth would receive so much energy that the surface temperature would rise to thousands of degrees within hours. The oceans would evaporate. The atmosphere would be stripped away. The planet would be sterilized of every trace of life in a matter of days. The surface rock eventually melting and beginning to glow from absorbed radiation. All of this, the scale, the luminosity, the violence of the conditions made Scuti the reigning champion of stellar size for years. It was the benchmark, the outer limit, the thing that made other large stars feel small. When astronomers wanted to convey the upper extreme of what a star could be, Scuti was the reference point they reached for. It appeared in popular science articles and YouTube videos and textbooks as the definitive answer to the question, what is the biggest star? But science does not deal in definitive answers. It deals in current best measurements, subject to revision as instruments improve and surveys extend further into the galaxy. And the galaxy, as it turns out, had been hiding something else, something larger, something that would make Scuti that staggering, planet-swallowing, solar system-spanning Hypergean look, by comparison, like a modest object. Not dramatically smaller, not a rounding error, but smaller in a way that would force everyone who had accepted Scuti as the outer limit to recalibrate, to extend their mental ceiling, to accept that the universe had not yet finished revealing the extremes of what was possible. The discovery did not come from pointing a telescope at a known giant and finding a measurement error. It came from a survey of an entire stellar population, a rich, dense, extraordinary cluster of stars sitting deep in the galactic plane, shrouded in dust, difficult to observe, inconspicuous from Earth's perspective, utterly remarkable from any other. A cluster called Stephenson 2, and one of the stars within it, designated simply as the 18th object in the catalogue, would turn out to be the most colossal single star ever measured by human instruments. To understand what Stephenson 2 to 18 is, we first need to understand where it lives. We need to go to the cluster. We need to understand why this particular region of the galaxy is so extraordinary, why it produces objects on this scale, and what the discovery of Stephenson 2 to 18 tells us not just about one star, but about the processes that shape the upper limits of what stars can become. The light you would need to look at Stephenson 2 to 18 tonight left that star approximately 19,000 years ago. That is not a figure inserted for dramatic effect. It is a fact about the geometry of the universe. The photons currently entering your eyes, should you somehow be able to see it, which requires infrared instruments, given the intervening dust, departed their source when Homo sapiens were still hunters and gatherers, tens of thousands of years before the first city, before the first written word, before the first agricultural field. We are not looking at a star. We are looking at a message from a star, dispatched long before any of the things we call civilization had begun. Now we need to go there. The year is 1990. The place is a mountaintop observatory in the high desert of Chile, where the air is thin and dry, and the astronomical term for atmospheric stability, for the stillness of the air column between telescope and sky, is among the best on Earth. A team of astronomers is conducting a systematic survey of the inner Milky Way, scanning the dense star fields near the galactic center, cataloging clusters and associations that are difficult to study from northern hemisphere observatories because they sit so close to the southern horizon. The work is methodical, unglamorous, the kind of survey astronomy that rarely produces immediate headlines but forms the essential foundation upon which more dramatic discoveries are eventually built. You map what is there before you can begin to understand what you are looking at. Charles Bruce Stephenson was an American astronomer who spent much of his career at the Warner and Swayze Observatory in Ohio. He was known primarily for his work on cataloging peculiar stars and star clusters, the kind of patient, systematic observational work that populated the reference databases that other researchers relied on for decades. Stephenson was not a theorist constructing grand models of stellar evolution. He was a cataloger, a mapper, a recorder of the sky's inventory. He identified and logged thousands of stars and clusters during his career. Many of them assigned his name in the astronomical literature, a quiet form of immortality, your surname attached to an object that will outlast every human civilization. Stephenson 2, the cluster relevant to our story, was identified during survey work and entered into the literature as a notable grouping of stars in the direction of the constellation Scutum, the same general region of sky that hosts UY Scuti, both objects embedded in the rich star-forming regions along the inner spiral arm of the Milky Way. For years after its identification, Stephenson 2 attracted modest interest. It was known to be a relatively young cluster, young in stellar terms, meaning tens of millions of years old, rather than billions, located at a distance of approximately 19,000 light-years from Earth, deep in the galactic plane. The galactic plane is the flat disk of the Milky Way, the region where stars are most densely packed, where gas and dust are most abundant, where star formation is most active. It is also, for observers on Earth, the most difficult part of the sky to study in visible light. The same dust that provides the raw material for new stars also absorbs and scatters the light of existing stars, dimming them, reddening them, obscuring entire populations of objects that would otherwise be readily visible. Stephenson 2 sits behind enough interstellar dust that in visible wavelengths, the light that human eyes can detect many of its stars are essentially invisible. Studying it requires infrared telescopes, instruments sensitive to wavelengths of light that penetrate dust more readily than visible light does, wavelengths that carry the thermal signature of cool, bright objects that dust cannot fully hide. When astronomers began conducting systematic infrared surveys of the inner galaxy in earnest, particularly with the advent of wide-field infrared cameras mounted on large telescopes in the 1990s and 2000s, Stephenson 2 came into sharper focus. And what emerged from that sharpening focus was remarkable. The cluster contains an extraordinary concentration of red supergiant stars, in a region of sky that, in visible light, appears as nothing much in particular. A slightly denser patch of a generally dense star field, infrared imaging revealed a population of massive, evolved, luminous stars of a type that is rare anywhere in the galaxy. Red supergiants are the swollen, cool descendants of massive main sequence stars. They represent a relatively brief phase in a massive star's life, lasting perhaps a few 100,000 years, during which the star, having exhausted the hydrogen fuel in its core, expands to enormous size. Because this phase is short compared to the main sequence lifetime, and because massive stars are themselves relatively rare, finding many red supergiants clustered in the same location is statistically unusual. It implies that the cluster is the right age old enough for the most massive stars to have evolved off the main sequence and expanded into red supergiants, but young enough that they have not yet exploded as supernovae, and that it was originally rich in massive stars. Stephenson 2 satisfied both conditions. With an age estimated at around 17 to 20 million years, it falls squarely in the window where stars initially more massive than approximately 15 to 20 solar masses have evolved into red supergiants, while the cluster has not yet been depleted of these objects by supernova explosions. And crucially, the cluster appears to have formed a large number of these massive stars in the first place, a consequence of the particular conditions in this region of the inner galaxy where gas densities are high, turbulent motions are energetic, and the formation of massive stellar objects is favored over the formation of the small, numerous, low-mass stars that dominate most regions of the galaxy. Detailed studies of Stephenson 2 published in the 2000s and 2010s identified more than 24 red supergiant stars within or associated with the cluster. 26 is the figure most commonly cited in the literature, though membership criteria and distance measurements introduce some uncertainty into the exact count. In any case, the number is extraordinary. To put it in perspective, the entire Milky Way galaxy, containing somewhere between 100 and 400 billion stars, is estimated to host perhaps a few thousand red supergiant stars at any given time. They are rare objects. They burn bright and fast and die young by stellar standards. Finding 26 of them in a single cluster, all formed from the same molecular cloud at approximately the same time, is the astronomical equivalent of finding a city in the middle of a desert, an anomalous concentration of unusual things that immediately demands explanation. This concentration made Stephenson 2 one of the most studied young, massive clusters in the Milky Way. Teams of astronomers from institutions in Spain, Germany, the United Kingdom, Chile, and the United States all turned their instruments toward it, each attempting to characterize the individual stars, to measure their temperatures and luminosities and radii and masses, to understand the dynamics of the cluster, to assess whether it was gravitationally bound or slowly dispersing, to map its extent and its stellar population in as much detail as current technology allowed. The work was painstaking. The dust made every measurement uncertain, correcting for the reddening effect of interstellar dust, the way dust preferentially absorbs shorter wavelengths of light and makes stars appear both dimmer and redder than they actually are, required careful modeling and substantial assumptions, each of which propagated uncertainty into the final results. Within this context of sustained, careful, multi-wavelength study, one particular object kept appearing at the extreme end of the measurements. One star among the several dozen candidates associated with Stephenson 2 consistently returned size and luminosity, estimates that were not merely large, not merely comparable to Ui Scuti or other known hypergiants, but larger, measurably, significantly, defensibly larger. The 18th catalogued object in the Stephenson 2 field, Stephenson 2 to 18, sometimes written as Saint 2-18 or RSGC 2-18 or Stephenson 2 DFK 1 inch, some catalogue systems, a star so embedded in the complexity of the cluster's extended halo that separating its properties from those of neighboring objects required multiple independent analysis techniques before the results could be trusted. The paper that drew widespread attention to the extraordinary scale of Stephenson 2 to 18 was published in 2020, authored by a team led by astronomers at the Instituto de Astrofísica de Canarias in Spain. The paper brought together infrared photometry measurements of the star's brightness in multiple infrared wavelength bands with spectroscopic observations that allowed the team to characterize the star's surface, temperature, and with distance estimates derived from the cluster's known properties and from parallax measurements available through the European Space Agency's Gaia satellite mission. Working through the analysis carefully, correcting for dust, accounting for measurement uncertainties, and cross-checking results with multiple independent methods, the team arrived at a radius estimate of approximately 2,150 solar radii for Stephenson 2 to 18, 2,150 solar radii, When those results circulated through the astronomical community first, through pre-publication sharing among researchers, then through formal peer review, then through the published paper itself, the response was a combination of careful professional scrutiny and, beneath the measured language of scientific discourse, something that might reasonably be described as awe. The number was large enough to invite skepticism, large enough that reviewers and critics examined the methodology in detail, looking for errors in the dust correction, questioning the distance estimate, probing the spectral classification for inconsistencies. This is how science works. An extraordinary claim is subjected to extraordinary scrutiny. The measurement is tested from multiple angles before it is accepted. The scrutiny has not overturned the result. The figure has been refined and debated. Some analyses suggest the radius may be somewhat smaller, in the range of 1,900 to 2,000 solar radii, while others are consistent with the higher estimates, but the consensus that emerged from the subsequent years of study is that Stephenson 2 to 18 is, within current measurement capabilities, the largest known star, larger than UY Scuti, larger than VY Canis Majoris, another frequently cited contender, larger than every other candidate in the catalogues, the new record holder, the object that reset the upper boundary of what we thought a star could be. It is worth pausing here to appreciate the process by which this discovery was made. Nobody pointed a telescope at Stephenson 2 to 18 and immediately saw something extraordinary. The star is invisible to the naked eye, buried behind 19,000 light-years of obscuring material. It did not announce itself. It was found through decades of patient survey work, through the application of new infrared instruments to old catalogue targets, through careful, quantitative analysis that translated photons into physical parameters, through peer review and argument and cross-checking and revision. The discovery of the largest known star was not a dramatic moment of revelation. It was a slow, collaborative, methodical accumulation of evidence that eventually converged on an answer that nobody had been expecting. That is what modern astronomy looks like. It looks like databases and Python scripts and conference papers and long email threads between collaborators on different continents working from data taken by robotic telescopes on mountaintops in Chile and the Canary Islands. The romance of the lone genius at the eyepiece, seeing something no one has seen before, belongs largely to the past. What replaced it is something less visually dramatic, but, in its own way, more impressive. A global, interconnected, self-correcting enterprise of knowledge production that has extended human sight to the edges of the observable universe and found, in the process, objects like Stephenson 2 to 18 objects that should not exist, that strain the theoretical models, that push the boundaries of what stellar physics can explain. To find the largest star in the universe, we did not send a probe. We did not build a portal. We did not travel anywhere. We gathered light. Ancient light departed from its source before the pyramids existed, before agriculture existed, before the domestication of the first animal, before writing, before the wheel, before fire was reliably controlled. We gathered that ancient light with mirrors and lenses and photon detectors. We fed it through spectrographs. We ran it through mathematical models calibrated against our understanding of atomic physics, and we extracted from it a number 2,150 solar radii that tells us something true about an object 113 quadrillion miles away. That capability, the ability to measure, to extract knowledge from ancient light, is perhaps the most extraordinary thing about the human animal. Not the size of Stephenson 2 to 18. The size is just a fact about the universe, and the universe does not care whether we know it. What is remarkable is that we do know it, that we could know it, that a species that evolved to track prey across grasslands and remember the locations of seasonal fruit trees somehow developed the intellectual and technological machinery to measure the diameter of a star 19,000 light-years away. But knowing the number is not the same as understanding the number. Knowing that Stephenson 2 to 18 has a radius of 2,150 solar radii is not the same as comprehending what 2,150 solar radii means. The number needs to be translated. It needs to be broken apart, examined from multiple angles, held up against things you already know, so that the abstract measurement can become something your mind can actually feel. That translation is what comes next. We are going to take this number apart piece by piece. We are going to build a picture of Stephenson 2 to 18 from the inside out. We are going to look at what it means for a single object to be this large, what its surface looks like, what its interior conditions are, what its light output implies, what happens to the space around it, what the physics of its existence tells us about the extreme boundary conditions of stellar structure. We are going to understand not just how big it is, but what being this big means. Get ready, because the numbers in the next section will do something to your sense of scale that the largest object you have ever stood next to, a mountain, a skyscraper, an ocean, could not prepare you for. 2,150 solar radii. Let us begin there. Let us take that number and refuse to let it remain abstract. Let us press on it from every angle until it yields something your mind can hold. The Sun's radius, as we established, is approximately 432,000 miles. Multiply that by 2,150, and you arrive at a radius of approximately 929 million miles. That is the distance from the center of Stephenson 2 to 18 to its surface. Not the diameter, the radius, the halfway point, the distance from the middle to the edge. The full diameter, the span from one side of the star to the other, measured through the center, is approximately 1.858 billion miles, nearly 2 billion miles, side to side, through the body of a single star. Now, place that star where the Sun currently sits. Place it at the center of our solar system, at the exact position occupied by the Sun right now, and ask a simple question: what happens to the planets? Mercury, the innermost planet, orbits the Sun at an average distance of roughly 36 million miles. It is consumed without ceremony. It does not approach the surface of Stephenson 2 to 18. It does not skim the outer atmosphere. It is simply inside the star, deep within it, orbiting in a region of plasma so dense and energetic that the concept of a planet existing there becomes physically meaningless. Venus orbits at approximately 67 million miles, inside, gone. Earth at 93 million miles, inside. The surface you are sitting on, the air you are breathing, the water in the oceans and the clouds in the sky, and the magnetic field that deflects the solar wind, all of it, submerged inside the body of Stephenson 2 to 18, at a distance from the star's center that represents barely 1/10 of its total radius. Earth would not fall to the center. It would dissolve. The densities and temperatures even in the outer layers of a red hypergiant, where the material is extraordinarily diffuse by the standards of a stellar interior, are sufficient to ablate and vaporize any planetary body within timescales so short they barely register. Earth would be gone before its orbit had completed a single degree of arc. Mars, at 142 million miles, inside. The asteroid belt, that broad ring of rocky debris between Mars and Jupiter, spanning from about 186 to 370 million miles from the Sun, inside. Jupiter, the king of the planets, at 484 million miles, inside. The gas giant that contains 318 Earth masses of material, whose great red spot is a storm that has persisted for centuries, whose magnetic field is 14 times stronger than Earth's inside the body of Stephenson 2 to 18, with hundreds of millions of miles of star still above it. Saturn, at 886 million miles, getting closer to the surface now. Depending on which radius estimate you use for Stephenson 2 to 18, Saturn sits close to, or just inside the star's photosphere, the visible surface layer. Saturn's rings, those extraordinary structures of ice and rock spanning 175,000 miles in width, orbiting a gas giant that itself spans 74,000 miles across both the planet and its entire ring system, would be, at most, grazing the outermost atmospheric layers of Stephenson 2 to 18. Uranus, at 1.78 billion miles, would finally be outside. Neptune, at 2.8 billion miles, safely beyond the star's reach. So, to be precise, if Stephenson 2 to 18 replaced our Sun, every planet from Mercury through Saturn, 6 of the 8 planets in the solar system would be inside the star. The entire inner solar system, the middle solar system, and the gas giants that dominate the outer solar system would be swallowed. Only the 2 outermost ice giants, Uranus and Neptune, along with the dwarf planets and the distant debris of the Kuiper Belt and Oort cloud, would survive as external bodies. Every planet capable of supporting life as we understand it, every rocky world in the habitable zone, every ocean world, every object with a solid surface and a reasonable temperature range gone, consumed, dissolved into plasma. The solar system, as a functioning architecture of orbiting bodies, would effectively cease to exist at the moment of substitution. Let that settle for a moment. Now, let us approach the size from a different direction. Let us think about light. Light travels at approximately 186,000 miles per second. This is not merely a fast speed. It is the maximum speed permitted by the laws of physics, the ultimate speed limit of the universe, the velocity that nothing with mass can reach and nothing without mass can exceed. In 1 second, a photon covers a distance greater than 7 times the circumference of the Earth. In 8 minutes and 20 seconds, it crosses the 93 million miles between the Sun and Earth. In about 4¼ years, it crosses the distance to the nearest star system, Alpha Centauri. How long does light take to cross the diameter of Stephenson 2-18? The diameter is approximately 1.858 billion miles. Divide by 186,000 miles per second. The answer is approximately 9,989 seconds, roughly 2 hours and 46 minutes. 2 hours and 46 minutes of light travel, side to side, through a single star. Think about what 2 hours and 46 minutes of light travel represents in terms you already know. In that same time, light could travel from Earth to the Sun and back the full 1.86 million mile round trip, approximately 10 times. 10 round trips between Earth and Sun while you cross one star. Or, consider it this way, in 2 hours and 46 minutes, light covers a distance roughly 20 times greater than the diameter of the entire orbit of Earth around the Sun, not the radius. The diameter, the full span of Earth's annual journey, 20 of those end to end, while a photon crosses Stephenson 2-18. If you wanted to fly across Stephenson 2-18 inches, the Parker Solar Probe, humanity's fastest spacecraft, moving at approximately 430,000 miles per hour at its maximum speed, the journey would take approximately 4,320 hours. That is 180 days, 6 months. And remember, you are inside a star. There is no vehicle, no heat shield, no material science that allows this. The thought experiment is not about practicality. It is about scale. 6 months at the fastest speed any human object has ever reached to cross the interior of a single star. Now consider the volume. Volume scales as the cube of the radius. Stephenson 2-18 has a radius 2,150 times that of the Sun. The cube of 2,150 is approximately 9.9 billion. Call it 10 billion. The volume of Stephenson 2-18 is approximately 10 billion times the volume of the Sun. 10 billion suns could fit inside Stephenson 2-18. Not metaphorically, not approximately. Within the volume enclosed by the photosphere of this single star, you could pack 10 billion objects, each the size of our Sun, and fill the space. We established earlier that 1.3 million Earths fit inside the Sun. 10 billion suns, each containing 1.3 million Earths, means that the volume of Stephenson 2-18 is equivalent to approximately 13, followed by 15 zeros, 13 quadrillion Earth volumes, 13,000 trillion Earths. If you stacked Earths on top of each other in a single column, and kept stacking until the column reached the volume of Stephenson 2-18, the column would be so long that light would take millions of years to travel from one end to the other. The number has broken free of meaning entirely. There is no useful mental image that corresponds to 13 quadrillion of anything. What these figures are doing is not providing you with a picture. They are demonstrating the failure of the human mind to picture it. They are showing you the boundary of your intuition, the point at which the numbers continue to be mathematically valid while ceasing to be psychologically meaningful. That boundary is, in itself, One of the most interesting facts about the human relationship with the cosmos. We can calculate things we cannot imagine. We can know things we cannot feel. The universe is under no obligation to fit within the scope of primate cognition. But let us continue pressing, because there are other dimensions of Stephenson 2-18 that illuminate its nature from different angles. The surface temperature. The photosphere of Stephenson 2-18, the layer from which visible and near-infrared light escapes, has a temperature of approximately 3,200 Kelvin. For reference, the Sun's photosphere sits at roughly 5,778 Kelvin. Stephenson 2-18 is substantially cooler at its surface than the Sun. This is the hallmark of a red supergiant. The enormous expansion of the outer layers spreads the star's energy over a vastly greater surface area, and in response to the lower energy density per unit area, the surface temperature drops. The star shifts from the blue-white of a hot compact star toward the deep red-orange of a cool extended one. If you could somehow stand outside Stephenson 2-18 and observe its surface, an exercise requiring you to survive conditions that would instantly vaporize any known material you would see, not the yellow-white disk of our sun, but a vast, dim, blood-red sphere extending across an impossible arc of sky, its surface mottled with convective structures of staggering scale. Those convective structures deserve attention. The sun's visible surface is covered in granules, convective cells where hot plasma wells up from below, spreads outward, cools slightly, and sinks back down. Each solar granule is roughly 600 to 1,000 miles across, and there are approximately 2 million of them covering the sun's surface at any given moment. In a red supergiant like Stephenson 2-18, the convective cells follow the same physical principle: hot plasma rising, cooling, sinking, but scaled with the star. Theoretical models and observational evidence from similar red supergiants suggest that a star like Stephenson 2-18 might have only a handful of convective cells covering its entire surface at once, not 2 million. Perhaps 3 or 5 or 10. Each one would be enormous beyond any useful comparison. A single convective cell on Stephenson 2-18 might span a region larger than the entire distance from the Sun to several planets combined. The surface of the star would not be the uniformly granulated texture of the Sun's photosphere. It would be a small number of vast, slowly churning structures, rising and falling on timescales of years or decades, rather than the Sun's 8 to 10 minute granule lifetime. This is one of the reasons that measuring the radius of red supergiants is so challenging. The surface of a star like Stephenson 2-18 is not a clean, sharp boundary. It is a region, a thick, extended, dynamic layer of plasma where density drops gradually and the behavior of light transitions from opacity to transparency. The photosphere is more of a zone than a surface. Different measurements, optical, infrared, spectroscopic probe, different depths within this zone, and the results can differ by meaningful amounts depending on exactly which layer is being measured. When astronomers report a radius of 2,150 solar radii, they are reporting an estimate that incorporates assumptions about the stellar atmosphere, the dust environment, and the distance, each of which carries uncertainty that propagates into the final figure. The measurement is the best current estimate. It is not a fact as crisp as the distance from New York to Los Angeles. It is a carefully derived number with error bars, subject to revision as better data arrive. But even at the lower end of the credible estimates, even if the true radius turns out to be closer to 1,900 or 2,000 solar radii, Stephenson 2-18 remains the largest known star, and its scale remains beyond ordinary comprehension. Now consider its luminosity. The total power output of Stephenson 2-18, the total amount of energy it radiates per second across all wavelengths, is estimated at approximately 440,000 times the Sun's luminosity. The Sun's luminosity is itself an extraordinary number, approximately 3.8 times 10 to the power of 26 watts, that is 380 trillion watts. Every second, the Sun pours that energy into surrounding space. Stephenson 2 to 18 radiates 440,000 times as much. Every second, the energy output of Stephenson 2 to 18 is equivalent to approximately 440,000 suns, all burning simultaneously. To translate this into something more visceral, the sun deposits approximately 1.4 kilowatts of energy on every square meter of Earth's surface facing it directly. That is the solar constant, the energy per unit area per second that drives weather, ocean circulation, photosynthesis, and ultimately all life on this planet. If Stephenson 2 to 18 sat at the same distance from an imaginary Earth, the energy arriving at that planet's surface would be 440,000 times greater. Not 440,000 kilowatts per square meter. That figure is itself incomprehensible, but consider what 440,000 times the solar energy input implies. The surface temperature of that imaginary Earth would rise to thousands of degrees within minutes. The rock would melt and begin to glow. The planet would behave less like a world and more like a secondary radiating surface, absorbing enormous quantities of energy and re-emitting them as heat. Nothing like biochemistry could persist. Nothing like an atmosphere could be retained. The planet would be, in the most literal sense, roasting in the continuous radiation of a star that is simply too powerful for ordinary matter to survive nearby. And yet Stephenson 2 to 18 is not a massive star in the conventional sense. Its current mass is estimated at somewhere between 15 and 40 solar masses, a meaningful range of uncertainty, again reflecting the difficulty of the measurements and the corrections required. This might seem surprisingly modest for an object of such extraordinary size, but this is precisely the point. Mass and radius are not simply proportional in stars. The relationship between them is complex, mediated by the physical processes happening in the stellar interior, and it changes dramatically as a star evolves. A star does not remain the same size throughout its life. It starts compact and dense on the main sequence, and if it is massive enough, it expands enormously during the red supergiant phase, not because more mass has been added, but because the interior structure reorganizes in response to changes in the energy source at the core. On the main sequence, the hydrogen-burning phase that dominates most of a star's lifetime, there is a balance. Gravity pulls inward, trying to compress the star into a smaller and denser object. Radiation pressure and thermal pressure push outward, the product of the enormous energy generated by fusion in the core. For as long as fusion continues at a sufficient rate, the outward pressure matches the inward pull of gravity exactly, and the star maintains a stable size. This balance is called hydrostatic equilibrium, and it is the fundamental reason that stars exist as discrete objects rather than either collapsing into black holes or dispersing into diffuse clouds of gas. Hydrostatic equilibrium is the uneasy truce at the heart of every star in the universe, and it holds for as long as the fuel lasts. When the hydrogen in the core runs out, the truce breaks down. The core, now composed primarily of helium and no longer generating the energy needed to maintain outward pressure, begins to contract under its own gravity. As it contracts, it heats. The rising temperature eventually ignites hydrogen in a shell surrounding the inert helium core, a new fusion zone, burning not at the center but in an expanding shell around it. The energy output from this shell fusion is, paradoxically, greater than the energy output from the original core hydrogen burning. The star becomes more luminous, and the outer layers, responding to this increased energy output from below, begin to expand. They expand far. For a massive star, one with tens of solar masses, the expansion is dramatic. The outer layers, pushed by the increased radiation pressure from the shell-burning interior, flow outward over timescales of tens of thousands of years, spreading across an ever larger volume of space, cooling as they go. The star's surface, once hot and compact, becomes cool and extended. Blue-white becomes orange, becomes red. A compact massive star becomes a red supergiant. And in the most extreme cases, the cases where the initial mass was very high, where the shell burning is particularly energetic, where the stellar winds that carry mass away from the surface are particularly intense, the result is an object like Stephenson 2 to 18, an object so distended that its outer layers are more atmosphere than star, a photosphere spread across nearly 2 billion miles of space, a tenuous giant hanging in the darkness, with the quiet implausibility of something that has been inflated beyond what physics should reasonably permit. Understanding this mechanism, understanding that the size of Stephenson 2-18 is not evidence of exceptional mass, but of exceptional evolution, an object that has been pushed to the outer boundary of what stellar structure can sustain, is essential for appreciating what it represents. Stephenson 2-18 is not simply a very big star. It is a star at an extreme, a star that has pushed the hydrostatic equilibrium truce to its limit, where the outward pressure barely wins against the inward pull of gravity, where the outer layers are so loosely bound that stellar winds carry significant mass away from the surface continuously, where the star is in a sense actively unraveling, losing material, evolving, changing, moving toward a destiny that will end this phase of its existence with extraordinary violence. That destiny is coming, not on any human timescale, not in any time frame that any civilization we might build would survive to witness, but on astronomical timescales, which are long but not infinite. Stephenson 2-18 is not a permanent fixture of the sky. It is a temporary state, a phase, an episode in a much longer story that began long before the light now reaching us departed from its surface, and that will end in a way that will briefly outshine entire galaxies. Every star begins the same way, not with light, but with darkness, with cold, with silence. Scattered throughout the Milky Way, drifting between the visible stars, are vast regions of gas and dust, so cold and so dense that they block the light from the stars behind them. From Earth, these regions appear as dark patches against the luminous band of the galaxy gaps in the starfield, places where the sky goes quiet. Astronomers call them molecular clouds, because within them the temperature is low enough, often just 10 to 30 degrees above absolute zero, for individual atoms to bond together into molecules: hydrogen, carbon monoxide, water, ammonia, and dozens of more complex organic compounds. These clouds are enormous. A single molecular cloud can span hundreds of light years, can contain enough mass to form millions of stars, can persist for tens of millions of years without significant change. They are the raw material of the universe's stellar population, the reservoirs from which every star that has ever burned was drawn. Inside these clouds, conditions are not perfectly uniform. There are denser regions, clumps where the gas and dust are more concentrated, perhaps disturbed by the shockwave from a nearby supernova, or compressed by the passage of a spiral arm density wave, or simply rendered unstable by the accumulation of enough mass in one place that gravity begins to win against the thermal pressure pushing the gas outward. When gravity wins, when a clump becomes dense enough that it can no longer support itself against its own weight, it begins to collapse, slowly at first, then faster still, as the increasing density strengthens gravity's pull and the timescales of collapse compress. As the cloud collapses, it heats. This is the same principle that heats a bicycle pump when you compress air rapidly. The work done by gravity is converted into thermal energy, and the temperature of the collapsing gas rises. The collapse is not perfectly uniform, angular momentum, the same property that makes a spinning figure skater speed up when she pulls her arms inward, causes the infalling gas to rotate faster as it concentrates. The result is not a single point, but a disk, a rotating, flattening structure of gas and dust with a dense, hot concentration at the center. This central object is a protostar, not yet a true star in the full sense, but a gravitationally bound, radiating body that is steadily growing as infalling material continues to add to its mass. For a protostar that will eventually become a star like Stephenson 2-18, a star with tens of solar masses, the collapse is rapid and violent by stellar standards. High-mass protostars accrete material quickly, their gravity strong enough to pull in gas from a wide surrounding region, and they reach the temperatures and densities needed to ignite hydrogen fusion in their cores while they are still embedded in their natal cloud, still surrounded by the gas and dust from which they formed. A massive protostar can ignite fusion and become a true star in as little as 100,000 years, extraordinarily fast compared to the millions of years required for a low-mass star like the Sun to reach the same milestone. Once nuclear fusion ignites in the core, the star enters the main sequence. Hydrogen fuses into helium. The energy released establishes hydrostatic equilibrium. The star stops contracting and settles into a stable configuration that it will maintain for as long as its core hydrogen supply lasts. For the star that will become Stephenson 2 to 18, with an initial mass perhaps in the range of 20 to 40 solar masses, the main sequence lifetime is brief, perhaps 5 to 10 million years. Brief, that is, by stellar standards. 5 to 10 million years is still a span of time so vast that it encompasses the entire evolutionary history of the genus Homo many times over. But compared to the Sun's 10 billion year main sequence lifetime, it is a flash. A candle burned at both ends, brilliant and short. During the main sequence, a massive star is a violent, powerful object. Its surface temperature runs to tens of thousands of Kelvin blue-white, intensely luminous, radiating enormous quantities of ultraviolet light. The radiation pressure from this ultraviolet output is so intense that it drives powerful stellar winds, streams of particles flowing outward from the surface at thousands of miles per second, carrying mass away from the star continuously. A massive main sequence star can lose a significant fraction of its total mass through stellar winds alone during its main sequence lifetime. The material it sheds enriches the surrounding interstellar medium with processed elements, the products of fusion, spreading the star's chemistry into the surrounding region before the star has even reached the end of its life. When the core hydrogen is exhausted, when the central region of the star has converted its hydrogen to helium and can no longer sustain the fusion reactions that have been the source of the star's outward pressure, balance shifts. The core contracts. The temperature rises. Shell hydrogen burning begins around the inert helium core. The outer layers expand. The star leaves the main sequence and begins its journey across the Hertzsprung-Russell diagram, the fundamental map of stellar properties that plots luminosity against temperature, moving rightward and upward, growing cooler at the surface as it grows larger in volume, brightening in total luminosity as the shell burning intensifies. This is the beginning of the red supergiant phase. And for a star destined to become something like Stephenson 2 to 18, the expansion continues beyond what most massive stars achieve, pushing the outer layers further and further from the core until the star occupies a volume that its main sequence self would not have predicted. The timescales of this expansion are long tens of thousands of years, but on the scale of the star's total lifetime, the transition is relatively rapid. The star spends most of its life as a compact, hot, blue main sequence object, and a relatively small fraction of its total lifetime as the bloated, cool red hypergiant that we observe today. Inside the red supergiant, the story continues. The helium that has accumulated in the core, the ash of the hydrogen fusion that powered the main sequence, is itself a fuel, but it requires higher temperatures and pressures to ignite. As the helium core contracts and heats, it eventually reaches the conditions needed to begin helium fusion. In the triple alpha process, one of the most improbable and beautiful reactions in nuclear physics, 3 helium nuclei fuse in a 2-step process to produce a single carbon nucleus. This reaction requires an extraordinary coincidence of nuclear energy levels, a resonance that the physicist Fred Hoyle predicted must exist before it was measured, reasoning that the universe clearly contained carbon, and therefore the reaction to produce it must be possible. He was right, and the resonance he predicted was subsequently found experimentally. Without this nuclear coincidence, carbon could not be produced inside stars in any significant quantity. Without carbon, the chemistry of life as we know it could not exist. The fact that we are here to notice this is, in some sense, a consequence of a particular property of the carbon, 1,2 nucleus, that was established in the first moments of the universe. Helium burning produces carbon and oxygen. When the helium in the core is exhausted, the same pattern repeats. The core contracts, heats further, and ignites the next fuel. Carbon burning produces neon, magnesium, and sodium. Neon burning produces oxygen and magnesium. Oxygen burning produces silicon, sulfur, and phosphorus. Each stage burns faster than the last because the energy yield per unit mass decreases with each successive fusion reaction, and the star must burn more fuel, more rapidly, to maintain the outward pressure needed to resist gravity. The star develops a layered structure, an onion of shells, each shell fusing a different element, each interior shell burning at higher temperature and greater density than the one outside it. The process accelerates as heavier elements are produced. Hydrogen burning, for a star like Stephenson 2-18, might last millions of years. Helium burning lasts hundreds of thousands. Carbon burning lasts perhaps 1,000 years. Neon burning, months. Oxygen burning, roughly a year. Silicon burning, the final stage before the end, lasts approximately 1 week. 1 week for the silicon in the core to be converted into iron peak elements, primarily iron and nickel, and in that week, the star reaches the threshold beyond which physics offers no further reprieve. Iron is the end of the road. The fusion of elements lighter than iron releases energy. That is why fusion has been powering the star throughout its life. But the fusion of iron absorbs energy rather than releasing it. Iron sits at the peak of the nuclear binding energy curve, the point at which neither fission nor further fusion yields a net energy gain. When the core of a massive star becomes predominantly iron, when it reaches the Chandrasekhar mass limit, roughly 1.4 times the mass of the Sun, packing that mass into a sphere, perhaps the size of Earth, the outward pressure that has held the star up against gravity for its entire life simply stops. Not gradually. Suddenly, the iron core collapses. In less than 1 second, in a fraction of a second, the core implodes, compressing from a sphere the size of Earth to a sphere roughly 12 to 15 miles across. The density at the center reaches and exceeds nuclear density, the density at which individual protons and neutrons are packed as tightly as they can be, touching each other with no space between them. At this density, a teaspoon of material would weigh approximately 1 billion tons. The collapse is halted abruptly, violently, by the short-range nuclear force, which resists further compression. The infalling material bounces off this incompressible core like a wave hitting a seawall. The bounce sends a shockwave outward through the star. The shockwave stalls, losing energy as it moves through the dense infalling layers above the core. But neutrinos, ghostly particles produced in enormous quantities during the core collapse, particles so weakly interacting that they pass through ordinary matter, almost as if it were not there, deposit a small fraction of their enormous energy into the stalled shockwave. This fraction is small in percentage terms, but enormous in absolute terms. The neutrino burst from a core collapse event carries more energy than the Sun will radiate across its entire 10 billion year lifetime, concentrated into 10 seconds. Even capturing 1% of that energy is sufficient to revive the shockwave and drive it outward with devastating force. The result is a core collapse supernova. The outer layers of the star, the enormous, diffuse, extended envelope of gas that has been expanding for hundreds of thousands of years, are blasted outward at velocities of 10 to 30,000 kilometers per second. The explosion is visible across billions of light years. For a period of days to weeks, the supernova can outshine the entire galaxy in which it resides, hundreds of billions of stars, each one burning steadily, their combined light overwhelmed by a single stellar death. At its peak, a typical core collapse supernova radiates approximately 10 billion times the luminosity of the Sun. The energy is staggering in its totality. Roughly 10 to the power of 44 joules more energy than the Sun will radiate in its entire lifetime, delivered in a matter of seconds. What remains at the center depends on the mass of the collapsing core. For many massive stars, the remnant is a neutron star, the 12 to 15-mile sphere of nuclear density material that formed during the collapse, spinning rapidly, threaded with magnetic fields trillions of times stronger than Earth's, pulsing with beams of radiation that sweep the sky like a cosmic lighthouse. A neutron star contains roughly 1.4 solar masses of material, the mass of hundreds of thousands of Earths, compressed into an object the size of a city. If you could place a neutron star in orbit around Earth, its gravitational influence would be sufficient to raise tides that would strip the oceans off the surface and draw them into space. For more massive progenitors, stars that began their lives with particularly high masses or whose cores exceed a certain threshold during collapse, even the nuclear force is insufficient to stop the implosion. The core continues to collapse past nuclear density, past any physical state that current theory can fully describe, into a singularity, a point of infinite density, clothed in an event horizon from which not even light can escape. A black hole forms. The surrounding stellar material, the vast envelope of gas that has been the star's body for hundreds of thousands of years, either falls into the black hole or is expelled in a powerful jet, a gamma-ray burst, a flash of high-energy radiation visible to telescopes billions of light-years away, lasting seconds to minutes, briefly the most energetic event in the observable universe. Stephenson 2-18 will almost certainly end in one of these two ways. Its current mass, somewhere in the range of 15 to 40 solar masses, places it in the regime of stars that die as core collapse supernovae. Whether the remnant is a neutron star or a black hole depends on details of the mass and the physics of the collapse that cannot currently be determined with precision, but the endpoint is not in doubt. Stephenson 2-18 will, at some point in the future, exhaust the fuel available to it, collapse, and explode. The enormous, bloated, red object that currently occupies a volume of 10 billion suns will be obliterated in a fraction of a second, the outer layers hurled into space at a significant fraction of the speed of light. A flash of light visible across galactic distances, a moment of violence so extreme that it will briefly outshine everything else in the Milky Way combined. When will this happen? The honest answer is that we do not know precisely. Stephenson 2-18 is already in the red supergiant phase, which means it has exhausted its core hydrogen supply and is in the later stages of its life. Red supergiants are, on cosmic timescales, relatively short-lived phenomena. A star typically spends perhaps a few 100,000 years as a red supergiant before either exploding or transitioning to another evolutionary phase. Given the age of the Stephenson 2 cluster, approximately 17 to 20 million years, the star has likely been a red supergiant for some fraction of that time, and the remaining time before its death could range from tens of thousands to a few 100,000 years. Compared to the age of the universe, that is a geological eye blink. Compared to recorded human history, it is an eternity. The light from that explosion, when it comes, will take 19,000 years to reach us. It may have already happened. The star visible in our infrared sky right now, the object whose properties we have measured and catalogued and debated, may no longer exist as a red supergiant. The photons telling us it is still there are 19,000 years old. The news of its death, if it has already died, is somewhere between us and the star, traveling toward us at the speed of light, completely indifferent to our curiosity about it, arriving exactly when it will arrive, and no sooner. Human beings have witnessed supernovae before. The historical record is clear on this. In the year 1054 CE, Chinese astronomers recorded a guest star in the constellation Taurus, a new point of light that appeared suddenly, bright enough to be visible in daylight, persisting for weeks before fading. This was the supernova that created the Crab Nebula, a still expanding cloud of gas and energetic particles centered on a rapidly spinning neutron star. The remnant is roughly 10 light-years across today, nearly 1,000 years after the explosion, and the central pulsar spins 33 times per second, broadcasting beams of radiation across the galaxy, like a lighthouse driven by the residual energy of one of the most violent events in human history. Nobody alive in 1054 knew what they were seeing. They recorded it faithfully, noting the position, the brightness, the duration. The recording survived. The understanding came later. In 1604, Johannes Kepler observed a supernova in the constellation Ophiuchus, the last supernova observed with the naked eye in our own galaxy. Kepler was not merely a passive observer. He was in the middle of a years-long effort to understand the motions of the planets, a work that would eventually overturn the Ptolemaic model of the solar system and establish the 3 laws of planetary motion that bear his name. When the new star appeared in October of 1604, Kepler turned his attention to it, observing it carefully over many months, noting how its brightness changed over time, arguing from its behavior that it was a true star, far beyond the sphere of the planets, and not merely an atmospheric phenomenon as Aristotelian cosmology would have preferred. His observations contributed to the gradual dismantling of the old cosmological order and the construction of the new one, a cosmos of vast distances and physical laws rather than crystalline spheres and divine arrangement. No supernova visible to the naked eye has been recorded in the Milky Way since Kepler's. The most recent supernova observed in a relatively nearby galaxy within our immediate cosmic neighborhood was SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way at a distance of approximately 168,000 light-years. Astronomers had not been expecting it. The progenitor star, the object that exploded, had been catalogued and studied, classified as a blue supergiant rather than the red supergiant that conventional theory predicted would explode. When it detonated on the 23rd of February 1987, detectors in underground laboratories in Japan and the United States neutrino observatories built for other purposes registered a burst of approximately 20 neutrinos in the space of a few seconds, arriving hours before the optical brightening. This was the first direct neutrino detection from a stellar event beyond our solar system, confirming in exquisite detail the theoretical picture of core collapse that theorists had been constructing for decades. The neutrinos told us that in the core of that dying star, a neutron star had formed. The light and heat of the explosion told us what the outer layers were doing. SN 1987A was, in scientific terms, one of the most illuminating astronomical events of the 20th century. The next naked-eye supernova in our own galaxy could come from any number of candidate stars. Betelgeuse, the red supergiant in Orion that has been showing unusual brightness variations, is perhaps the most famous. Eta Carinae, a massive and unstable system in the southern sky, is another strong candidate, and Stephenson 2-18, buried behind its curtain of dust, is almost certainly not visible to the naked eye, even when it explodes. The intervening dust will absorb and scatter the optical light from the explosion, though infrared and radio telescopes will detect it. When Stephenson 2-18 dies, those watching the right instruments in the right wavelength bands will see something extraordinary. The rest of the world may not notice. But the explosion itself is not the end of the story. It is, in a profound sense, the beginning of the next chapter. Because what a supernova does is not merely destroy a star. What it does is disperse the star's accumulated chemistry into the surrounding interstellar medium, creating the raw material for the next generation of stars, the next generation of planets, the next generation of chemistry that may, somewhere, under the right conditions, give rise to something that can look back at the sky and ask where it came from. The elements fused in the interior of Stephenson 2-18, the carbon, the oxygen, the neon, the silicon, the sulfur, the iron will, when the star explodes, be thrown outward into the surrounding galaxy. They will mix with the surrounding gas. They will eventually cool, condense, and become part of new molecular clouds. Those clouds will collapse. New stars will form from them, and some of those stars may have planets. And on some of those planets, under conditions that we do not yet fully understand, but are beginning to piece together, chemistry may organize itself into structures of sufficient complexity to replicate, to metabolize, to evolve into life, into minds, into creatures that will one day look up at the night sky and wonder where the iron in their blood came from. It came from here, from stars like Stephenson 2-18, from the interior of objects so large that our entire solar system would fit inside them, burning at temperatures of millions of degrees, fusing light elements into heavy ones across timescales that make civilizations seem like afterthoughts. The iron in your hemoglobin, the calcium in your bones, the oxygen in every breath you draw, all of it was forged in the core of a massive star that lived and died long before the sun existed and scattered into space by the explosion that ended that star's life. You are, in the most literal and precise chemical sense, made of stellar ash. The atoms in your body are the remnants of ancient stellar deaths, and the star we have been studying tonight will, when it dies, become the raw material for something else, something we cannot predict, cannot observe, cannot know. Another star, perhaps, another chemistry, another improbable arrangement of matter that may, one day, be alive. 19,000 light-years. That is the distance between you and Stephenson 2 to 18, not 19,000 miles, which would be less than the circumference of the Earth. Not 19,000 kilometers, which is roughly the distance from London to Sydney and back. 19,000 light-years. 19,000 times the distance that light moving at 186,000 miles per second, covering nearly 6 trillion miles in a single year, travels in an entire year. The number is so far outside the range of anything a human being has ever physically traversed that the word distance begins to feel inadequate. Distance implies something you could in principle cross, given enough time and resources. What separates us from Stephenson 2 to 18 is not merely distance in that ordinary sense. It is a gulf so deep that it makes the entire span of human civilization look like a rounding error. Let us begin with the most basic translation. 1 light-year is approximately 5.88 trillion miles. 19,000 light-years is therefore approximately 111.7 quadrillion miles. 111,000 trillion miles. If you wrote that number out in full 111 quadrillion, 700 trillion miles and printed it on a standard sheet of paper, the number itself would fit on a single line, but there is no physical experience, no journey, no act of travel available to human beings that corresponds to that figure. It is a number that exists in the mathematics of astronomy and nowhere else in human experience. Consider what 19,000 years means in terms of human history. The light currently arriving at Earth from Stephenson 2 to 18, the photons that are entering infrared telescopes right now, being captured by photon detectors and converted into data that astronomers analyze in papers and conference presentations, those photons departed from their source approximately 17,000 BCE, 17,000 years before the Common Era. At that moment in human history, the last ice age was still in progress. Glaciers covered large portions of North America and Northern Europe. The ancestors of all living human beings were scattered in small nomadic bands across Africa, parts of Asia, and Europe, living entirely by hunting and foraging, with no agriculture, no permanent settlements, no writing, no mathematics, no astronomy. The domestication of the dog had barely begun. The wheel did not exist. The concept of a city was not yet imaginable. And from Stephenson 2 to 18, photons were departing, setting out on their 19,000-year journey across the darkness, aimed at nothing in particular, destined to arrive at a small rocky planet that did not yet have observers equipped to receive them. Those photons traveled for 19,000 years. During that time, the entire history of human civilization unfolded. Agriculture was invented, independently, in multiple regions of the world. Cities grew from the first permanent settlements along river valleys in Mesopotamia, in Egypt, in the Indus Valley, in China. Writing was developed, mathematics was formalized, philosophy was born. Empires rose and fell. The pyramids were built and weathered into their current state. Rome rose and fell. The medieval period unfolded. The Renaissance, the scientific revolution, the industrial revolution, 2 world wars, the invention of the transistor, the first nuclear reactor, the first satellite, the first human in space, the first telescope sensitive enough to detect an infrared source 19,000 light-years away in a dust-obscured cluster and measure its properties with sufficient precision to characterize it as the largest known star. All of that happened while the light was in transit. The photons did not wait for us to be ready. They simply traveled. They were indifferent to the civilizations rising and falling in the tiny blue speck toward which they were moving, indifferent to the questions those civilizations would eventually develop the capacity to ask, indifferent to the instruments those civilizations would eventually build to receive them. They simply moved, at the speed of light, through the interstellar medium for 19,000 years. And when they arrived, we were here, with telescopes, with the mathematics to interpret what they carried, with the curiosity to ask what object had sent them and how large it was. This is one of the most philosophically vertiginous aspects of observational astronomy. We do not see the universe as it is, we see it as it was. Every observation is a message from the past, its age determined by the speed of light and the distance of the source. When you look at the moon, you see it as it was approximately 1.3 seconds ago. When you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago. When you look at the nearest star, Alpha Centauri, you see it as it was 4 years and 3 months ago. When you look at the Andromeda Galaxy, the nearest large galaxy to the Milky Way, visible to the naked eye as a faint smudge on a dark night, you are looking at light that departed its source 2.537 million years ago, when our ancestors were Australopithecines walking the savannas of Africa, before the genus Homo had yet emerged, before stone tools had been invented. And when you look at Stephenson 2 to 18 through the infrared instruments needed to penetrate the intervening dust, you are looking at an object as it existed 19,000 years ago. The star you see is not the star that exists now. The star that exists now is 19,000 years further along in its evolution. Its surface has shifted, its mass has changed slightly, shed continuously through stellar winds. The convective cells on its surface have risen and fallen and risen again thousands of times. And possibly this is not a dramatic speculation, but a genuine possibility grounded in the star's evolutionary state. It no longer exists at all. The supernova may have already happened. The flash of light from the explosion may already be traveling toward us, a message 19,000 light-years away and closing, with no way for us to know it is coming until it arrives. We are, in the most precise sense, looking at a ghost, an image of something that may no longer exist, preserved in the ancient light that departed from it before a single city had been built on this planet. Now consider the question of travel. Not as a practical proposal, no serious person proposes sending a spacecraft to Stephenson 2, 18 inches, any near-term future, but as a thought experiment designed to give physical substance to the distance. To make the number 19,000 light-years mean something your body can feel, not just your mathematics can process. Let us start with Voyager 1. Launched by NASA in September of 1977, Voyager 1 is the most distant human-made object ever constructed. As of the early 2020s, it had traveled approximately 14 billion miles from Earth, far enough to have crossed the heliopause, the boundary where the Sun's influence on the surrounding interstellar medium gives way to the broader interstellar environment. Voyager 1 has, in the most technical sense, left the solar system. It is in interstellar space, and it is moving at approximately 38,000 miles per hour, roughly 330 million miles per year. At that speed, how long would it take Voyager 1 to reach Stephenson 2 to 18? The distance is approximately 111.7 quadrillion miles. Divide by 330 million miles per year. The answer is approximately 338 million years. 338 million years. The last time that much time elapsed on Earth, the Permian extinction, the greatest mass extinction in the planet's history, the event that killed more than 90% of all marine species and 70% of all terrestrial vertebrate species, had not yet happened. The dinosaurs had not yet evolved. The first mammals were tens of millions of years in the future. The continents were arranged in configurations unrecognizable to modern eyes. 338 million years of Earth history would need to pass before Voyager 1, continuing at its current speed, with no course correction and no deceleration, reach the location of Stephenson 2 to 18. And Voyager 1 is not even pointed at Stephenson 2 to 18. It is moving in a completely different direction. Now consider a faster spacecraft. The Parker Solar Probe, at its closest approach to the Sun, reaches speeds of approximately 430,000 miles per hour. This is roughly 11 times faster than Voyager 1. At that speed, maintained continuously ignoring the fact that the Parker Solar Probe only achieves these speeds briefly at perihelion and spends the rest of its orbit moving far more slowly. The journey to Stephenson 2 to 18 would take approximately 29.7 million years, nearly 30 million years. The first primates appeared on Earth roughly 60 million years ago, half the time since the first primate walked the Earth, at the fastest speed any human-made object has ever achieved. To cross the distance to a single star, what would a spacecraft traveling at the speed of light take? Not 30 million years, not 300 million years, 19,000 years. 19,000 years at the absolute physical maximum of velocity, the speed that nothing with mass can reach, the speed that requires infinite energy to approach. Even in the ultimate theoretical limit, constrained only by the laws of physics and not by the limitations of any technology we can build, the journey takes 19,000 years, longer than all of recorded human history. You could not send a probe to Stephenson 2 to 18 and expect news of its arrival within any civilization's lifespan. You could not send a probe and expect the civilization that launched it to still exist when the probe sent back its first signal, which would itself take another 19,000 years to return. The universe does not care about our timescales. It was not designed for our convenience, our curiosity, or our ambition. The distances are what they are. The speed of light is what it is. The gap between what we want to know and what we can directly reach is measured not in miles or years, but in geological epochs and evolutionary timescales. We are creatures who live for roughly 80 years, who have been building instruments for a few centuries, who have been launching spacecraft for a few decades, and we are trying to understand objects that are 19,000 light-years away, whose light departed before the invention of pottery. And yet, we have measured its radius. We know its temperature. We know its luminosity. We know roughly how massive it is and approximately how old its cluster is and approximately how much longer it has before it dies. We know the physics of what is happening in its core right now, not from direct observation, because no light from Stephenson 2 to 18's core has ever reached us and never will, but from the mathematical framework of stellar physics that we have built and tested against thousands of other stars over more than a century of astrophysics. We know things about the interior of Stephenson 2 to 18 that we cannot know about the interior of the Earth in comparable detail. The irony is precise. The planet we live on keeps its deep interior more hidden from us than a star 19,000 light-years away does, because the Earth's interior neither emits nor transmits light, while a star's interior physics is encoded in the light that escapes from its surface. This is the extraordinary thing about physics as a tool of knowledge. It does not require you to go somewhere to understand it. It requires you to understand the laws that govern matter and energy everywhere, and then to read the evidence those laws leave in the signals that reach you. A spectrum of light, analyzed carefully, tells you the temperature, the chemical composition, the velocity, the magnetic field strength, and in many cases, the physical size of the object that emitted it. You do not need to visit a star to know what it is made of. You need only capture its light and understand the language in which that light is written. Spectroscopy, the science of breaking light into its component wavelengths and reading the absorption and emission lines that different atoms leave as fingerprints, is arguably the most powerful single scientific technique ever developed. It extended the reach of human knowledge from the neighborhood of Earth to the edge of the observable universe, from the nearest stars to the most distant galaxies, transforming astronomy from a science of positions and motions into a science of physics and chemistry and history. The photons reaching us from Stephenson 2 to 18 right now carry information about a star as it existed 19,000 years ago. They carry that information faithfully, undistorted by the passage of time, carrying the spectral fingerprints of the elements present in the star's atmosphere, the thermal signature that encodes the surface temperature, the subtle shifts in wavelength that reveal the star's velocity relative to Earth. By the time those photons entered the atmosphere and were collected by a telescope mirror, they had traveled an incomprehensible distance, but they arrived intact. They arrived carrying their information, and we had built the tools to read it. There is something almost unbearably poignant about this. The star sent out its light not knowing, not caring, that anything would receive it. The light asked no permission and sought no destination. It expanded outward in all directions, most of it traveling into an emptiness so profound that it will never encounter another particle of matter in any meaningful time frame. The fraction that happened to be aimed at this particular solar system, at this particular planet, at this particular moment, that fraction was vanishingly small, and yet it arrived, and we were here to catch it. And from it, we extracted a measurement that told us something true about an object 111 quadrillion miles away. That is not nothing. That is in fact one of the most remarkable things any entity in the known universe has ever done. Right now, as you read or listen to these words, photons from Stephenson 2 to 18 are falling on the mirrors of telescopes in Chile, in the Canary Islands, in space. Infrared detectors are converting those photons into electrical signals. Software is processing those signals into data. Astronomers are analyzing that data, comparing it to theoretical models, refining their understanding of the star's properties, publishing their findings in journals that other astronomers read and build upon. The conversation between the star and humanity is ongoing. It has been ongoing since the first human being looked at the night sky and noticed that some points of light were different from others, variable perhaps, or distinctly colored, or surrounded by a faint haze. The conversation has been getting progressively more precise, more detailed, more physically meaningful for centuries, and it is nowhere near finished. The light that departed Stephenson 2 to 18 yesterday in the star's reference frame will not arrive at Earth for another 19,000 years. By then, if any descendants of ours are here to receive it, they will have instruments we cannot imagine and knowledge we cannot anticipate. They will read that ancient light and find in it things we do not yet know how to look for. The conversation extends forward in time as well as backward. We are in the middle of it. We have always been in the middle of it. There is something the distance also gives us. Beyond the vertigo of its scale, it gives us perspective. Not the comfortable, reassuring kind of perspective that self-help books promise, the kind that is supposed to make your problems seem small and manageable. A different kind of perspective. A harder kind. The kind that comes from understanding your actual position in a structure so vast that 19,000 light-years is a local measurement. A distance to a neighbor in the same galactic neighborhood, a number that does not even register on the scale of the full observable universe. Because Stephenson 2 to 18 is not at the edge of the galaxy. It is not even close. It is 19,000 light-years away in a galaxy that spans approximately 100,000 light-years across. Stephenson 2 to 18 is in our galactic neighborhood, relatively speaking in the same general region of the Milky Way's disk as our solar system, separated from us by a distance that represents roughly 1/5 of the galaxy's total diameter. The galaxy extends much further in all directions. Beyond the galaxy, there are other galaxies. Beyond the local group, the cluster of galaxies of which the Milky Way is a member, there are other groups, other clusters, other superclusters. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The Virgo cluster, the nearest large galaxy cluster, is approximately 65 million light-years distant. The observable universe extends approximately 46 billion light-years in every direction from Earth. Not because the universe is only 46 billion light-years across, but because the expansion of space itself means that light from more distant regions has not yet had time to reach us. 19,000 light-years, in this context, is a local measurement, a neighborhood distance, a short hop, and even at this neighborhood distance, a journey at the fastest human speed takes 30 million years. The universe is built on scales that make the word incomprehensible mean something. Not merely very large, not merely difficult to visualize, genuinely, structurally incomprehensible to a mind evolved for the African savanna, a mind that navigates by the positions of trees and rivers and the faces of other humans, a mind that tracks events on timescales of years and distances on scales of miles. The gap between the universe's scales and the mind's scales is not a failure of imagination. It is a structural feature of our situation. We evolved in a particular niche, on a particular planet, in a particular epoch. That niche did not require us to directly perceive things 19,000 light-years away. The fact that we can know about them at all, that we have developed the mathematics and the instruments and the conceptual frameworks to reach across distances that our unaided senses cannot bridge, is not something to be taken for granted. It is the result of thousands of years of cumulative intellectual effort, of a tradition of inquiry that passes its results from one generation to the next, building and refining and correcting, extending the reach of human understanding further and further into the dark. That tradition is the most fragile and most valuable thing our species has ever produced. More fragile than any civilization, more valuable than any treasure. It can be interrupted. It can be lost. Entire bodies of knowledge have been lost before libraries burned, traditions broken, the cumulative achievements of generations scattered by war or neglect, or the slow erosion of institutions. The knowledge we have of Stephenson 2-18 and of every other object in the night sky exists because a chain of transmission has held unbroken from the first person who noticed the variability of a distant star to the astronomers publishing papers on infrared photometry in 2020. Every link in that chain matters. The star at the end of that chain 19,000 light-years away, burning through its final fuel reserves, preparing in its own geological timescale for a death that will briefly illuminate the galaxy, knows nothing of this. It does not know we exist. It did not know the first astronomer who catalogued it. It does not know about the papers written about it, the debates over its radius, the calculations of its luminosity. It simply burns, as it has burned for millions of years, and will continue to burn until the iron accumulates in its core and the truce with gravity finally breaks. But we know about it, and knowing is its own kind of connection, not physical, not causal, but real in a way that matters enormously, at least to us. We are 19,000 light-years away from the largest known star, separated from it by a distance that no technology we possess could bridge in any meaningful time frame, unable to visit it, unable to touch it, unable to do anything about its eventual fate. And yet we know what it is. We know its size, its temperature, its luminosity, its mass, its evolutionary state, its probable future. We have taken the ancient light it sent us without intention and extracted from it a precise and detailed portrait of an object more colossal than anything else our instruments have yet found. That knowledge is ours, freely held, requiring nothing from the star in return. There is a ladder, not a physical ladder, not a structure you can climb, but a conceptual one, a sequence of scales ascending from the smallest to the largest, each rung separated from the one below it by a factor so large that arriving at the next level requires abandoning everything your mind built to comprehend the previous one. We have been climbing this ladder throughout this journey, and we are not yet at the top. We have looked at the sun and found it vast. We have looked at Scuti and found the sun small. We have looked at Stephenson 2-18 and found Scuti modest. Now we need to keep climbing, not because the exercise is comfortable, it is not, but because the full picture of where Stephenson 2-18 sits in the structure of the cosmos and where we sit relative to it is essential to understanding what the largest known star actually means. Begin at the bottom of the stellar ladder, not with the sun, which we have already established is average, but with the smallest objects that qualify as stars at all, a red dwarf. Proxima Centauri, the nearest star to our solar system, is the most familiar example. It sits 4.24 light-years away, so close, in cosmic terms, that it is practically a neighbor, and yet still so far that the fastest spacecraft humanity has ever built would take 70,000 years to reach it. Proxima Centauri has a radius of approximately 0.15 solar radii, 15% of the Sun's radius. It is a dim, cool, reddish object, barely large enough to sustain hydrogen fusion, burning so slowly and carefully that it will remain on the main sequence for approximately 4 trillion years, roughly 300 times the current age of the universe. If the universe were a single day old, and the Sun had already lived its entire life and died, Proxima Centauri would still be a young star, with most of its life ahead of it. Red dwarfs are the most common type of star in the galaxy. Perhaps 70 to 80% of all stars are red dwarfs, and they burn with an extraordinary patience that makes the Sun's 10 billion year lifespan seem reckless and brief. Now compare. Proxima Centauri has a radius of 0.15 solar radii. Stephenson 2-18 has a radius of 2,150 solar radii. The ratio between them is approximately 14,333. Stephenson 2-18 is more than 14,000 times larger in radius than the nearest star to our solar system. In terms of volume, where the difference scales as the cube of the ratio, Stephenson 2:18 is approximately 2.9 trillion times the volume of Proxima Centauri. 2.9 trillion. If you filled Stephenson 2:18 with objects the size of Proxima Centauri, you would need nearly 3 trillion of them to fill it completely. 3 trillion of the most common type of star in the galaxy, packed inside one object. Every red dwarf in the Milky Way, if you counted them all, perhaps 160 billion, assuming 70% of the galaxy's roughly 230 billion stars are red dwarfs, would fill Stephenson 2:18 approximately 50 times. 50 complete fillings of the largest known star, using every red dwarf in the entire galaxy. This is the spread of stellar sizes. From Proxima Centauri, barely holding itself together at the lower edge of stellar physics, to Stephenson 2:18, inflated beyond what seems physically plausible, the range spans 14,000 in radius and nearly 3 trillion in volume. The universe does not deal in narrow distributions. It deals in extremes separated by factors that make ordinary arithmetic feel inadequate. Now step back further. Step back far enough that individual stars cease to be meaningful objects, and the galaxy itself becomes the unit of consideration. The Milky Way, our galaxy. The system of stars, gas, dust, dark matter, and everything else gravitationally bound to the same central structure. Viewed from outside as we can only imagine it, since no spacecraft has ever left the Milky Way and no telescope has ever photographed it from beyond its boundaries, it would appear as a flattened spiral disk, perhaps 100,000 light-years across and roughly 1,000 light-years thick at the disk, with a central bulge swelling to perhaps 10,000 light-years in height, and spiral arms curving outward from the central bar in patterns shaped by density waves and the collective gravitational dynamics of hundreds of billions of stars. The solar system sits in one of these spiral arms, the Orion arm, sometimes called the Orion spur, approximately 26,000 light-years from the galactic center. We are not at the center, we are not at the edge. We are in the middle suburbs of an unremarkable spiral galaxy, roughly halfway between the dense central bulge and the sparse outer reaches of the disk. Stephenson 2:18, at 19,000 light-years from Earth, sits roughly 7,000 light-years closer to the galactic center than we do deeper in the disk, embedded in the denser star-forming regions of the inner Milky Way, where gas is more abundant and star formation more active. If you were to mark both the solar system and Stephenson 2:18 on a map of the Milky Way drawn at a scale of 1 inch per 1,000 light-years, the two marks would be separated by less than an inch. On the full map of the galaxy, which would span approximately 8 feet across at that scale, the distance between us and the largest known star would be a gap you could bridge with your thumb. The Milky Way contains, as best we can estimate, somewhere between 100 and 400 billion stars. The uncertainty in that figure is substantial, counting the stars in your own galaxy from the inside through layers of obscuring dust and across distances where individual stars blur into the collective glow of the background is extraordinarily difficult. But whether the number is 100 billion or 400 billion, it dwarfs anything that human intuition can process directly. If you counted one star per second without stopping, no sleeping, no eating, no pausing, counting 100 billion stars would take approximately 3,170 years. If the count began at the fall of the Roman Empire, it would not be finished yet. If you counted 400 billion, it would take nearly 12,700 years longer than all of recorded human history. Now, step back further. Step back until the Milky Way itself is a small object in a larger structure, the local group. This is the name given to the cluster of galaxies gravitationally bound to each other within a region of space roughly 10 million light-years across. The local group contains more than 50 individual galaxies, though most of them are small, dim dwarf galaxies barely distinguishable from large star clusters. The two dominant members are the Milky Way and the Andromeda Galaxy, each containing hundreds of billions of stars, orbiting their shared center of mass and slowly approaching each other. In approximately 4.5 billion years, roughly the same time the Sun has already existed, the Milky Way and Andromeda will begin to merge. not collide in the violent, explosive sense. The space between individual stars in both galaxies is so vast that actual stellar collisions will be extraordinarily rare during the merger. But the two galaxies' gravitational fields will interact, distorting both systems, pulling long tidal tails of stars into space, driving new waves of star formation as gas clouds in both galaxies are compressed by the encounter, eventually settling over billions of years into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. Neither the Sun nor anything near it is likely to be dramatically affected by this merger on a human timescale. The night sky will change. Andromeda, currently a faint smudge to the naked eye, will grow as it approaches, eventually spanning a significant arc of sky, but the direct gravitational effects on any individual star during the initial encounter are likely to be modest. The galaxy-scale dynamics of the merger will play out over billions of years. Stephenson 2 to 18 will have been dead for billions of years before the merger begins in earnest. Its supernova remnant will have long since dispersed into the interstellar medium, its atoms recycled into new stars, perhaps through multiple generations of stellar birth and death. The local group itself is a member of a larger structure. The Virgo supercluster, sometimes called the local supercluster, contains the local group along with many other galaxy groups and clusters within a region approximately 110 million light-years across. It is named for the Virgo cluster. At its center, a massive concentration of more than 1,000 galaxies, approximately 65 million light-years from Earth, the gravitational dominant of the broader supercluster. But even the Virgo supercluster, vast as it is merely one component of something larger still. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a remarkable paper in the journal Nature that redefined the boundaries of the supercluster to which the Milky Way belongs. Using data from surveys of galaxy velocities, the way galaxies move through space, their motions shaped by the gravitational field of the surrounding large-scale structure, Tully and his colleagues mapped the flow of galaxies across an enormous region of space and identified a coherent structure they named Laniakea, from the Hawaiian words meaning immeasurable heaven. Laniakea contains approximately 100,000 galaxies, spans roughly 520 million light-years, and has a total mass equivalent to approximately 10 to the power of 17 solar masses, 100 million billion suns. The combined gravitational influence of a structure so large that light takes 520 million years to cross it. Within Laniakea, the Milky Way is an unremarkable member of a minor subcluster. The local group, containing the Milky Way and Andromeda and their associated dwarf galaxies, is a small gravitational island in the outer regions of the supercluster, far from the dominant attractors that pull the bulk of the supercluster's mass. On a map of Laniakea, the local group would be a faint smudge in the corner, barely distinguishable from the background. And within the local group, the Milky Way is one of two large members. And within the Milky Way, the solar system is one of hundreds of billions of star systems. And within the solar system, Earth is one of 8 planets. And Stephenson 2 to 18, the largest known star, the record holder, the object we have been studying with such care, is one star in the Milky Way. One object in one galaxy, in one minor cluster, in one supercluster, in one region of the observable universe. The observable universe extends approximately 46 billion light-years in every direction from Earth. It contains an estimated 2 trillion galaxies, a number that was revised upward by a factor of 10 in 2016 when astronomers analyzing deep field images from the Hubble Space Telescope realized that earlier surveys significantly undercounted the number of small, faint, distant galaxies. 2 trillion galaxies, each containing, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at approximately 10 to the power of 24, roughly 1 septillion, 1 followed by 24 zeros. Stephenson 2 to 18 is one of those, 1 star out of 1 septillion, the largest one we have found, and almost certainly not the largest one that exists, given that we have surveyed only a tiny fraction of the stars even in our own galaxy. let alone the 2 trillion galaxies beyond. The perspective that emerges from climbing this ladder is vertiginous in a way that is difficult to describe and impossible to resolve. On one hand, the scale makes everything feel insignificant. One star out of a septillion, one planet around that star, one species on that planet, one individual. What could possibly matter at these scales? What could any human action, any human thought, any human life possibly mean against the backdrop of 2 trillion galaxies and 10 to the power of 24 stars? The universe is so vast, so old, so indifferent, that the entire span of human civilization, the pyramids and the cathedrals and the libraries and the wars and the art and the science and the love and the grief, all of it occupies a volume and a duration that is, measured against the full extent of the cosmos, essentially zero. This is the vertigo of scale, and it is real. It is not a logical fallacy or an emotional overreaction. The numbers are what they are. The universe is what it is. The insignificance is mathematical. But there is another way to look at the same facts. A harder way. A more interesting way. Consider what it takes for matter to know itself. Consider what has to happen in the universe for any part of it to become aware of its own existence, to look outward at the rest of the cosmos and ask questions about it. The universe is approximately 13.8 billion years old. For most of that time, it contained no minds. It contained hydrogen and helium forming into stars, burning, exploding, seeding the interstellar medium with heavier elements. It contained galaxies assembling under the influence of dark matter halos. It contained the gradual enrichment of the cosmic chemistry as generations of massive stars lived and died. It contained planets forming around second and third generation stars, inheriting the heavy elements produced by previous stellar generations. And eventually, on at least one of those planets, in at least one solar system, in at least one galaxy, the chemistry organized itself into something capable of reflection. That something is us. And among all the things that something has done, building cities, writing poetry, making war, making music, the thing that seems most extraordinary in the context of this particular story is the act of measurement. The act of looking at a point of infrared light 19,000 light years away and determining that it is a star with a radius of 2,150 solar radii. The act of extending human knowledge across a distance that dwarfs anything in our physical experience, using instruments built from materials forged in earlier stellar generations, powered by energy derived from nuclear reactions happening in our own star, operated by minds that evolved on a planet whose existence depends on the specific sequence of stellar deaths that produced the heavy elements in its crust and its oceans and its atmosphere. We are, in the most literal sense, the universe looking at itself, not metaphorically, not poetically, literally. The atoms in the brain of every astronomer who has ever analyzed the light from Stephenson 2 to 18 were forged in stellar interiors, dispersed by stellar explosions, swept up into the molecular cloud that became the solar nebula, incorporated into the planet Earth, and eventually organized by 4 billion years of biological evolution into a structure capable of abstract reasoning and mathematical analysis. The universe made those atoms in stars. The stars scattered those atoms into space. Gravity and chemistry and biology organized those atoms into scientists. And the scientists turned their instruments back toward the stars and read the universe's own history from the light it had been sending out for billions of years. This is the extraordinary paradox at the heart of the relationship between humanity and the cosmos. We are small, vanishingly, incomprehensibly small one species on one planet, around one star, in one galaxy, among 2 trillion. And yet we are the only part of the observable universe that we know of that has developed the capacity to understand any of it. The cosmos is vast and ancient and almost entirely indifferent to our existence. But we are paying attention. We are measuring. We are asking. We are building models and testing them against observations and revising them when they fail and building better ones. We are doing something that, as far as we can tell, nothing else in the universe is doing or has ever done, or perhaps will ever do again. That is not nothing. That is perhaps the most significant thing in the observable universe. Not because significance is a property of the universe itself, it is not. The universe does not deal in significance, but because we are the ones doing the evaluating, and by any measure we can apply, the capacity to understand is extraordinary. A rock cannot measure the radius of a star. A star cannot measure its own radius. Only a mind, only a structured arrangement of matter, complex enough to model other arrangements of matter, to represent reality in abstract terms, to ask questions and devise means of answering them, can do this. And in the entire observable universe, we know of exactly one place where such minds have arisen. One, Us, standing on a small rocky world, orbiting an average star in the outer regions of an unremarkable spiral galaxy, separated from the largest known star by a distance that no technology we possess could bridge in any meaningful time frame. We have nonetheless reached across that distance with mathematics and light and careful measurement and brought back something true, something real, something that expands the boundary of what is known in the universe, the boundary that exists, as far as we can tell, entirely within the minds of a single species on a single planet. Every time an astronomer analyzes a spectrum and extracts a temperature, every time a calculation converts photon counts into a physical radius, every time a paper is published and read and built upon by the next researcher, the boundary expands, the known grows. The darkness retreats not physically, not in any way that changes the universe itself, but in the map of the universe that exists in human minds. And that map, imperfect and incomplete and perpetually under revision, is the most remarkable structure in the observable cosmos. We are small, we are brief, we are fragile in ways that the universe demonstrates repeatedly and without mercy. But we look up, we measure, we remember, we pass the knowledge forward, and in doing so, we perform a function that, as far as the evidence shows, the universe is otherwise incapable of performing for itself. The question is whether we appreciate that, whether we protect that capacity with the urgency it deserves, whether we understand that the tradition of inquiry, the chain of transmission that connects the first person to notice the variability of a distant star to the astronomer, publishing a paper on Stephenson, 18 inches. 2020 is not merely an academic enterprise or a cultural luxury. It is the most essential thing we do. It is the thing that makes us, in a universe of blind and indifferent forces, something other than just another arrangement of matter waiting to be dispersed. The ladder goes higher than Laniakea, higher than the observable universe. Possibly current cosmological models suggest the full universe may be far larger than the observable portion, perhaps infinite in extent, with our observable region a mere bubble of causal connectivity in an unimaginably vaster whole. We do not know, we may never know, if the expansion of the universe continues to accelerate and the light from regions beyond our current horizon recedes beyond any possibility of detection. There may be aspects of the cosmos that are structurally inaccessible to us, not because our instruments are inadequate, but because the universe itself has placed them beyond the light horizon. We do not know what lies beyond what we can see. We do not know whether the universe is finite or infinite. We do not know whether the physical laws that govern the observable universe are universal or local, whether other regions of the cosmos, if they exist, operate under different constants, different parameters, different rules. We do not know whether complexity anywhere else in the universe has organized itself into something capable of asking these questions. We do not know whether, in 2 trillion galaxies containing septillions of stars, we are alone in our capacity for reflection, or whether the universe is thick with minds of which we are simply unaware. We do not know, and in not knowing, we are doing the only thing that is available to us, continuing to measure, continuing to analyze, continuing to extend the boundary of what is known, one observation at a time, one paper at a time, one carefully extracted number at a time. The largest known star sits 19,000 light-years away, burning through its final fuel reserves, indifferent to our attention, and we are here, watching, measuring, understanding. That is where we stand on the ladder, somewhere between the quantum and the cosmic, between the red dwarf and the supercluster, between the atom and the observable universe. Small enough to be humbled by everything above us on the scale, large enough, in precisely one respect, to comprehend all of it. We began with the sun. That seems like a long time ago now. It seems like a different scale of thinking, a different set of expectations about what the universe contains and what our place in it might be. We began with the sun because the sun is the star. We know the one whose light falls on our faces every morning, whose energy drives the weather and the seasons and the photosynthesis that built every living thing on this planet. We began there because it is the natural starting point, the reference from which all stellar comparisons must ultimately be made. The sun is not small. We established that carefully. Its diameter of 865,000 miles dwarfs the Earth by a factor of 109. Its volume contains 1.3 million Earths. Its core burns at 15 million degrees Kelvin. It is, by any standard rooted in human experience, an object of staggering scale and power. And then we climbed, and the sun shrank. UY Scuti arrived, and the sun became a marble beside a basketball. Then Stephenson 2-18 arrived, and UY Scuti became a detail, a slightly larger marble beside, a structure so large that our entire solar system would be swallowed within it, that the orbit of Saturn would lie beneath its surface, that the light from one side of it takes 2 hours and 46 minutes to reach the other, that a spacecraft traveling at the fastest speed any human machine has ever achieved would require 6 months to cross its diameter alone, and billions of years to traverse the distance between us and it. This is what we found at the top of the stellar ladder. Not a comfortable answer, not a number that slots neatly into any framework the human mind was built to hold. Something else. A radius of 2,150 solar radii, a diameter of 1.858 billion miles, a volume 10 billion times the sun's, a luminosity 440,000 times greater than the star around which our world orbits, a surface temperature of 3,200 Kelvin, cool enough to be red, cool enough that the star glows like an ember, the size of a minor solar system, steady and vast and ancient and doomed. These are the numbers. They are correct to within the uncertainties that honest astronomy acknowledges. They were extracted from ancient light by careful instruments and careful minds, translated from photons into understanding through a century of accumulated physics, and they represent something true about the universe, something that was true 19,000 years ago, when the light that told us about them departed their source, and remains true now, and will remain true regardless of whether any mind exists to know it. But the numbers alone are not the point. The numbers are the doorway. What lies beyond the doorway is the understanding that the universe is not scaled to us. It was not designed with human intuition in mind. The distances, the temperatures, the timescales, the sizes, none of them bear any relationship to the scales at which human beings evolved to function. We are creatures of the middle distance, adapted to a world of meters and kilometers, of years and decades, of objects you can hold in your hand or see with your naked eye. The universe operates at scales that differ from ours, by factors ranging from the merely incomprehensible to the genuinely unrepresentable. And Stephenson 2-18, sitting at the extreme end of the stellar size distribution, larger than any other star we have measured, a red hypergiant in the late stages of a brief and violent life, is one of the universe's clearest demonstrations of how far its scales exceed ours. And yet the star is not alien to us. Not truly. Not in the way that matters most. Consider what Stephenson 2-18 is made of. Hydrogen, helium, in its outer layers, traces of heavier elements carbon, oxygen, nitrogen, the products of fusion reactions in previous stellar generations, swept up when the molecular cloud that gave birth to the Stephenson 2 cluster collapsed from the enriched interstellar medium, the same elements that make up the sun, the same elements that make up the Earth, the same elements that make up you. The chemistry is not exotic. It is the most common chemistry in the universe, the chemistry written into the periodic table that hangs on the wall of every high school science classroom on Earth. Hydrogen is hydrogen, whether it is burning in the core of Stephenson 2-18 or bonding with oxygen in the water in your cells. The physics does not change with scale. And consider what Stephenson 2-18 will do when it dies. It will explode. It will hurl the products of its long nuclear history, the carbon forged in the triple alpha process, the oxygen fused alongside it, the heavier elements built in the silicon burning that precedes the final collapse out into the interstellar medium at a significant fraction of the speed of light. Those elements will travel, they will mix with the surrounding gas, they will cool, they will condense, they will become part of new molecular clouds, and those clouds will collapse, and new stars will form, and some of those stars will have planets, and some of those planets will be rocky and temperate, and on some of those planets, over timescales measured in billions of years, chemistry will organize itself into something that breathes and grows and eventually looks up. This is the cycle, not a metaphor, not a philosophical gloss on otherwise cold physics, a literal description of how the universe operates. Stars are born from gas and dust. They fuse light elements into heavy ones. They die and scatter those heavy elements back into space. New stars form from the enriched material, new planets form alongside them, and the heavy elements, the carbon, the oxygen, the nitrogen, the iron, the calcium, the phosphorus become available for chemistry of increasing complexity, chemistry that eventually, given enough time and the right conditions, produces minds capable of tracing the cycle back to its source. The iron in your blood was forged in a stellar core. Not this star Stephenson 2-18 is still alive, its iron still accumulating in the core that will eventually trigger its collapse, but a star like it, a star with tens of solar masses, burning through its hydrogen in a few million years, expanding into a red supergiant, fusing elements in concentric shells, and finally exploding in a core collapse supernova that seeded the interstellar medium with the products of its long nuclear life. That star, or those stars, more likely, because the Earth's chemistry reflects the contributions of many stellar generations lived and died before the Sun was born, before the solar system existed, before the planet you are standing on had condensed from the disk of gas and dust that surrounded the young Sun, long before any of that. The atoms in your body are older than the Earth. Most of them are older than the solar system. They have been through stellar cores and supernova explosions, and the cold of interstellar space, and the heat of planetary formation, and the chemistry of the early oceans, and the long history of biological evolution, and they have arrived, temporarily, in the configuration that constitutes you. You are not separate from Stephenson 2-18 and the other massive stars that have burned and died across the history of the galaxy. You are downstream from them. You are what happens when their chemistry passes through enough generations of stars and planets and biology. You are, in the most precise and literal sense, made of the same material that they are made of, processed by the same nuclear physics, governed by the same laws. The boundary between you and the largest star in the known universe is a boundary of scale and complexity, not a boundary of substance. This is what the numbers, translated into understanding, ultimately reveal. Not merely that Stephenson 2-18 is large, though it is beyond any comfortable imagining. Not merely that the universe is vast, though it is beyond any useful analogy, but that the universe is a connected system, and that what happens in the core of a dying star 19,000 light-years away is, in a causal and chemical sense, directly relevant to your existence. The cosmos is not a backdrop against which human life plays out. It is the source of human life. The stars are not decoration. They are the factories that produced the atoms from which you are built, the processes that enriched the chemistry of the galaxy across billions of years until the conditions for biology were established, the engines of the cosmic cycle that made something like you possible. Knowing this changes nothing about the practical facts of your existence. The distance to Stephenson 2-18 remains 19,000 light-years. The star remains inaccessible to any technology we possess or can currently envision. Its eventual death will occur on timescales far beyond anything relevant to any civilization we can imagine, and the light from that death will take 19,000 years to reach us, and when it does, it will be, for most observers, simply a new point of light in the infrared sky. The universe will not pause to explain what it means. It never does. But you know what it means. You know because you have made the journey from the familiar warmth of the sun to the staggering dimensions of UY Scuti, to the incomprehensible scale of Stephenson 2-18, through the physics of stellar evolution and the violence of core collapse supernovae, and the distances that make every human timescale and every human speed feel negligible, up the ladder of cosmic scales from the individual star to the galaxy, to the supercluster, to the observable universe, and back down again to the single species on the single planet that has, somehow, developed the capacity to understand all of it. The universe did not give us this understanding. We built it. Slowly, painstakingly, across centuries of observation and calculation, across generations of scientists who lived brief lives and contributed what they could and passed the knowledge forward to those who came after them. Charles Bruce Stephenson, cataloguing infrared sources at the Burrell-Schmidt telescope in the 1980s and 1990s, did not know he was identifying the host cluster of the largest star in the known universe. He was doing careful, methodical work, the kind of work that does not make headlines in its own time, but becomes essential in retrospect, a foundation stone that later researchers build upon. The astronomers who published the 2020 paper characterizing Stephenson 2-18's extraordinary radius were themselves building on Stephenson's catalogue and the work of dozens of researchers before them. The knowledge is collective. It has always been collective. Every measurement stands on the shoulders of every previous measurement, and every measurement is temporary. This matters. Stephenson 2-18 is the largest known star. Known. The qualifier is not modesty, it is precision. The Milky Way contains hundreds of billions of stars, the vast majority of which have never been characterized in any detail. The regions of the galaxy most likely to harbor massive stars, the dense, dusty, star-forming regions of the inner disk, are precisely the regions most difficult to observe at optical wavelengths, requiring the infrared surveys that have only become technically feasible in recent decades. There may be another star, somewhere in the dust-obscured reaches of the galactic plane, larger than Stephenson 2-18. There is no theoretical reason to believe Stephenson 2-18 sits precisely at the maximum size that stellar physics permits. It sits at the maximum size that our current observations have found. That is a different statement. The record will almost certainly be broken, as UY Scuti's record was broken, as the records before UY Scuti's were broken. Science is not a collection of final answers. It is a process of successive approximations, each one more accurate than the last, each one simultaneously a genuine achievement and an acknowledgement that more remains to be learned. This is not a weakness of science, it is its defining strength, a system of knowledge that acknowledges its own incompleteness, that builds the mechanism of its own revision into its foundations, that treats the falsification of a previous claim not as a failure, but as progress, is the most reliable instrument for approaching truth that human beings have ever developed. The record held by Stephenson 2-18 will be broken not because science was wrong, but because science works. Because the instruments will improve, because the surveys will extend further into the dust, because the next generation of telescopes will see what the current generation cannot, because the tradition continues. Right now, as this moment passes, the light from Stephenson 2-18 is falling on the Earth. Photons that departed their source 19,000 years ago, when the last ice age still gripped the northern hemisphere, and the ancestors of every living human being were nomadic foragers on the African savanna, are arriving at this planet and entering the atmosphere and reaching the ground. Most of them fall unobserved on oceans, on ice, on uninstrumented landscapes, on the rooftops of cities where the light pollution obscures all but the brightest stars. A tiny fraction of them fall on the mirrors of infrared telescopes, are collected and focused and recorded, are converted into data that carries information about the star that sent them. And that data is, right now, being analyzed. Somewhere in a university office, in an observatory control room, on a laptop, in a coffee shop or a library or an apartment, an astronomer is looking at numbers that represent ancient light from the largest known star, asking questions about it, testing models against it, learning something from it that no one has known before. The conversation continues. It has never stopped. It will not stop. As long as there are minds willing to look up and instruments capable of reaching across the dark. 19,000 light-years away, a star larger than any other we have found burns on in the infrared dark. Its surface churns in convective cells larger than our entire solar system. Its core accumulates the iron that will eventually end it. Its outer layers shed mass continuously into the surrounding space, enriching the interstellar medium with the chemistry of its long life, seeding the future with elements that have not yet become planets, that have not yet become chemistry, that have not yet become anything at all except the raw material of what comes next. What comes next is unknown. It has always been unknown. The universe does not provide previews. It provides only the present moment and the ancient light of the past, and the mathematics to translate one into understanding of the other. We are here now. We are small and brief and improbable and extraordinarily capable of understanding things that have no direct bearing on our survival and no practical use beyond the expansion of what is known. We measure stars, we calculate distances, we trace the nuclear histories of elements from their formation in stellar cores to their incorporation into living cells. We build instruments sensitive enough to detect a single photon that has been traveling for 19,000 years and carry it through a focusing mirror and a detector and a processor and a pipeline into a number on a screen that tells us something true about the largest object we have ever found. That is what we do. That is what we have always done. From the first person who noticed that the bright point in Scorpius changed brightness in a regular pattern, to the infrared astronomers cataloging the dust-shrouded clusters of the galactic plane. We look, we measure, we remember, we pass it on. The star does not know we are watching. The star does not know anything at all. It burns because the physics requires it to burn. It will die when the physics requires it to die. It existed for millions of years before any mind arose anywhere in the galaxy capable of knowing about it. And it may exist for hundreds of thousands more years after our civilization is gone, its light traveling outward in all directions, finding no telescope to receive it, carrying information that no mind will ever decode. That is what we do. That is what we have always done, from the first person who noticed that the bright point in Scorpius changed brightness in a regular pattern, to the infrared astronomers cataloging the dust-shrouded clusters of the galactic plane. We look, we measure, we remember, we pass it on. The star does not know we are watching. The star does not know anything at all. It burns because the physics requires it to burn. It will die when the physics requires it to die. It existed for millions of years before any mind arose anywhere in the galaxy capable of knowing about it, and it may exist for hundreds of thousands more years after our civilization is gone, its light traveling outward in all directions, finding no telescope to receive it, carrying information that no mind will ever decode. But right now, in this narrow window of cosmic time, we are here. We have the instruments, we have the mathematics, we have the curiosity, and the patience, and the accumulated knowledge of centuries of careful observation, and we are paying attention. The largest star ever found sits 19,000 light-years away, embedded in its dusty cluster, vast and dim and ancient and temporary, and we know it is there. We know what it is. We know how it formed and how it burns, and how it will die, and what it will leave behind. In a universe of 10 to the power of 24 stars, spread across 46 billion light-years of observable space, across 13.8 billion years of time, in a cosmos that operated in total darkness for the first 100 million years of its existence, and has been building toward complexity through every stellar generation since, in all of that we know. That is not a small thing. That is perhaps the most extraordinary thing in the observable universe. A single candle burning in a darkness that has no edge, not permanent, not powerful enough to illuminate more than the tiniest fraction of what surrounds it, but burning, casting light, asking, as all fires do, what lies beyond the next circle of the dark. The answer is out there, 19,000 light-years away and further, deeper in the galaxy and beyond the local group and beyond Laniakea, and beyond everything we have yet reached with our instruments and our mathematics and our restless, extraordinary need to know. We have not stopped. We will not stop. Let us begin.